to the second day of the XAIP-Workshop. We have a invited talk from Francesca Toni that's about to come up. We then have a little break and a panel with all of our invited speakers, as well as with Tathagata Chakraborty, followed by a small break and the fourth paper session of the workshop, and then finally an invited talk by Bertram. But the talk coming up now is with Francesca Toni. Francesca is Professor in Computational Logic in the Department of Computing at Imperial College London, where she is a member of the Artificial Intelligence Research Team and the leader of the Computational Logic and Argumentation Research Group. She is also the Royal Academy of Engineering and JP Morgan Research Chair in Argumentation-Based Interactive Explainable AI, and she is a member of the GLAM Research Group and of the AI at Imperial Network of Excellence at Imperial College London, and the founding leader of the Centre for Explainable AI. Many thanks for being here, Francesca. We're really looking forward to hearing your talk.
Thanks, Benjamin, and thanks also, Silianos, for inviting me. It's a pleasure to be here. Can you see it properly? Right, so I'm going to talk about argumentation-based interactive explanations. And I'm going to start with telling you if it needs to be, why we need to worry about explainable AI. I guess probably the audience in this workshop does not need persuading. Nonetheless, I'm going to tell you a little bit about it, and also tell you maybe something that may need more work on why explanation as argumentation. I'll then kind of borrow from the interactionist view of reasoning by Mercier and Sperber, well-known theory of reasoning in psychology, to kind of push for explanations which are not just argumentative, but by being so are interactive as well. The kind of argumentation I am using is, of course, computational argumentation, which is positioned at the intersection of knowledge representation and reasoning in symbolic AI, multi-agent systems, as well as natural language processing and machine learning more generally. So that's the brief outline of what I'm planning to tell you about. So let's start with why we need to worry about explainable AI. I guess I am preaching to the converted nonetheless. It's well understood that AI can do a lot, but it really needs to have the humans in the picture to do what it can do at its best. There have been explainable AI activities sponsored all over the world, starting with DARPA's explainable AI program. The GDPR in the EU and the UK can be seen as pushing for the right to explanation, definitely pushes for transparent information and communication. Explainability is mentioned in all guidelines on ethical uses of AI, or trustworthy AI in this case. Governments have taken notice. This is the most recent national AI strategy in the UK, which came out last autumn, and as you can see, explainability is a strong concern. And the industry is also very much interested. For example, JP Morgan, with whom I collaborate, have an explainable AI Center of Excellence, to name just one example. So all in all, there is an obvious push for explainability for explainable AI. And that's indeed there to guarantee trustworthiness and to make sure that we know what we are using. So what kind of solutions are in existence out there? This is a nice overview by Arpeggio on what the landscape looks like. And you can see that according to their interpretation, at least, if you want a model agnostic way to provide explanations, then you have the usual sharp line, etc. You can have counterfactuals or adversarial examples as example-based kind of explanations, and you can have model-specific. According to their overview, interpretable models per se are explainable and do not need to be a worry for those of us who are interested in explainable AI. I beg to differ, and I will argue that interpretable models are not necessarily explainable and need to be explained nonetheless. So the most popular methods, the model agnostic and example-based, can be illustrated as follows with a very simple example, whereby a model predicts for a certain applicant for a credit card that it should be denied. Then there are two types of explanations that are quite popular in the literature. The kind of feature attribution ones, they would say the card was denied, for example, because the client is credit unworthy, despite having a good salary. And that's the kind of format that is basically at the core of approaches such as sharp and line. But you could also have counterfactual explanations, which are of the kind, that point to what change in the input would lead to a different output, thus pointing to which bits of the input are really crucial towards the output. In this particular case, a counterfactual explanation may say, for example, that had the client had a good credit score, then the card would have been granted. So these are just the kind of things that exist out there. There are other methods as well. Sorry, before I tell you about the other methods, let me point out that these kind of explanations are what can be called, and some people call, zero knowledge proofs. So they provide very shallow rationale. They just tell you which bits of the inputs are responsible for the output. And also they are one shot. So they rely upon a static delivery of information. In addition to this method, there are also approaches that use, sorry, I don't know what I did, apologies. That use surrogate or twin models that are interpretable per se. So, for example, so this kind of the vision is that you have a model, for example, black box model, and you have an equivalent in quotes interpretable model, possibly built from the same data that matches the output. And for example, this may rely upon the use of decision trees as interpretable models, as k-nearest neighbors, logic, decision graphs. I mean, this is just a non-exhaustive list of possible interpretable models can be used as surrogate twin models for an opaque one. And here is a very partial list of references of people that have proposed this view. In reality, my view is that interpretable AI systems also need explaining. And indeed, explainability has been around as long as general AI has been around. I mean, you can look, for example, at express systems that were kind of popular in the 70s and 80s in AI. An example is the Mycin system, using completely transparent rules as the basis of their conclusions. But even then, it was clear that one needed to explain these systems and provide explanations for them. So I guess I'm not the only one to believe that explainability and interpretability is in the eye of the beholder. And what mathematicians or computer scientists find explainable may not be what ordinary people, lay people, find explainable too. So overall, I believe that we need to worry about explainability, no matter what, no matter the opacity or otherwise of the underlying system being explained. Another aspect is the human angle, and in particular, whether we could or we should have just a one-size-fits-all explanation. And obviously the answer is no. Again, many of you may be aware of this. That's an example from IBM, who is very keen on explanation and explainability. Of course, if you are trying to explain why a certain application was turned down or accepted, you wouldn't want to produce different explanations if the receiver of explanation is a data scientist, a loan officer, or a bank customer, because these three types of users have very different needs and also mental models. So data scientists must ensure that the model works properly before deployment. The loan officer needs to assess the model's prediction and make the final judgment. And the bank customer simply wants to understand the reason for the application result and maybe go about changing that. I can see that there are 2 comments in the chat. All right, so no, they're nothing to do with this. So if you have any questions, please do stop me, unless they can wait until the end. Okay, so the question is whether the explanations, needs to be adjusted to the different users, and overall, I think there is broad agreement that they should. So the minute we put the users in the picture, we need to also consider, what humans do. And there is, again, broad understanding within our field that looking at how humans help each other can provide, or explain to each other, can provide useful information for designing explainable AI solutions. And Tim Miller in particular advocates that explainable AI should really be at the intersection of artificial intelligence, human-computer interactions, but also the social sciences. So let us look at the social sciences at this point, and let's see what the social sciences have to tell us. So I'm particularly interested in what Mercier and Sperber have to tell us, because they're pushing a view of reasoning which, in my mind, is really amenable to developing and designing explainable AI solutions. Their interactionist view of human reasoning is, in my mind, very much pushing towards a kind of explainable AI solutions that are interactive. So let's see what this interactionist view of reasoning is about. So the analysis of Mercier and Sperber relies upon the observation that people are pretty bad at producing reasons, but they are pretty good at evaluating the reasons of others. When they produce reasons, they're often biased. They mostly produce reasons for their own side, and they're lazy, so they're not very demanding towards their own reasons. But when it comes to evaluating the reasons of others, they are unbiased. They can even accept reasons that challenge their viewpoint if they are convincing, and they're very demanding. People are convinced only by good enough reasons. So, in the view of Mercier and Sperber, this analysis really is a nail in the coffin of the intellectualist approach, such as the approach advocated by Kahneman with the type 1 and type 2 of reasoning. And in particular, it's this kind of analysis that they perform goes against the kind of argument that the study of inference must be based on a general and formal understanding of norms of good inference. Because if that were the case, then why would we be so much worse at producing than at evaluating? Still about producing reasons. So in their view, the whole idea of a dual process, that intuitive inference and reasoning are achieved by 2 different types of mechanisms, is somewhat challenged by their own interactionist view of reasoning, that advocates that reasoning is not an alternative to intuitive inference, but is actually the use of intuitive kind of inferences for producing reasons, for about reasoning. And there is something else in their analysis that is useful, I think, in our setting. People use reasons to explain or justify decision already taken and beliefs already held. So this is a kind of post hoc retrospective use of reasons, which is very much what we often desire doing. We have a model and we want to provide explanations. That's a post hoc process. And they reiterate this, saying that reasons play a role in the after-the-fact explanation and justification of our intuition, not in the process of intuitive inference itself. So then a natural question in my mind, looking at their kind of focus on a certain form of explanation is whether we should really develop machines that they use reasons to explain their outputs, no matter how these outputs can be obtained. So basically seeing explanation as a form of reasoning on what the model is doing. And their analysis, the Mercier-Sperber's analysis, also points to strongly to the use of argumentation-based, dialogical, or conversational form of explanations that can help us design explainable AI solutions. So the viewpoint is that the normal conditions for the use of reasons are social and more specifically dialogic, and reasoning thrives in the back and forth of conversations when people can exchange arguments and counter arguments. So then a kind of natural question emerges as whether we should develop argumentative forms of explainable AI, which lend themselves to supporting dialogues or conversations between humans and machines. And actually, the push for argumentative solutions is also elsewhere in the social sciences, not just in Mercier and Sperber's interactionist view of reasoning. Here I'm quoting from other scholars in the social sciences that point to the fact that the majority of what might look like causal attributions turns out to look like argumentative claim markings. And if you think about it, a lot of the feature attribution-based explanations are really argumentative in spirit, at least. Think of a line explanation as indicated here. That's our input, its characteristics of a mushroom, and here is the output that the mushroom is poisonous. The line explanation in the middle points to features that are for poisonous, so they're kind of reasons or arguments for the predictions, and features that are against and for the other prediction, for the kind of conflicting prediction. So at least superficially, one could say that feature attribution explanations are argumentative in spirit. So all in all, I hope I've convinced you that it's worth looking at argumentative forms of explanations. And that's what I'm doing with quite a few collaborators. But of course, moving out of the social sciences and into computer science, we need to look at computational forms of argumentation. Actually, computational argumentation is a quite well worked out and developed field these days. It has been around at least since the early 90s, and there are many solutions and proposals that we can leverage upon in order to develop explainable AI solutions that are argumentative. So what is computational argumentation? I like to think of it as about solving an equation whereby we choose how to represent, how to abstract settings where conflicts are present. We then add ways to evaluate these debates and resolve the conflicts, and in such a way that certain properties are satisfied. So the abstractions of debates is what we call argumentation frameworks. The evaluation is what we call semantics, which comes with algorithms and systems implementing those. And then the properties may range from computational complexity properties to existence and more. So in the context of explainability, we use extensively one form of argumentation framework and semantics, which I'm going to illustrate very briefly with an example. Suppose we have a bunch of very short reviews about a hotel. The first review says the hotel is lovely, what a stunning spa, and that we can consider as an individual, as a single argument that I indicate, I label A1. The second review may say, you know, I'm not convinced the spa is too small, and that's another argument, A2, that disagrees with the first. The third argument, A3, is instead saying that the spa was something else, thus supporting the initial argument A1. Overall, this problem, which amounts to resolving conflicts between the reviews to identify a suitable hotel we want to book, this simple problem can be abstracted as a so-called bipolar argumentation framework, which can be visualized as a graph and includes as arguments A1, A2, A3, with an attack relation between A2 and A1, and a support relation between A3 and A1. So that's what the argumentation framework may boil down to, and this is an abstraction of the debate that goes on, that ignores what the arguments say, and focus on how they are related. So it's rather high level and abstract. In terms of semantics, we could use, I'm going to use it for the illustration here, what is referred to as a gradual semantics, which ascribes a dialectical strength to each argument, and that's a number in a certain range. Here I'm using a range 0, 1. And the kind of semantics I'm illustrating assumes that arguments have an intrinsic strength. So before the debate even starts, they have their own kind of what we call base code. So something that sanctions how good they are in isolation prior to considering dialectical relationships. And in this particular setting of reviews, this intrinsic goodness may come from votes, from people who have access to reviews. It could be that we know that there are an equal number of people agreeing with the first review. With the second review, more people think it's good, it's a good, valid review than not. And for the last argument, lots of people think that it's a valid review, lots more than people that think that it's not. So we can use this information to provide this intrinsic strength, which may be 0.5 for the first argument, 0.6 for the second, and 0.9 for the third. This is, again, the strengths are all within a range of 0.1, so the higher the better, the higher the stronger dialectic. Given this intrinsic strength and the dialectical relationships, semantics, gradual semantics, such as the one I'm illustrating here, compute a dialectical strength that takes into account the dialectical relationships and may, for example, say that given that this argument is strongly supported by a strong argument and attacked by a medium argument, should really have a higher strength than its intrinsic starting point. And here I've indicated also the calculations of what this could be. So you kind of, there are, the supporter is stronger than the attacker, therefore we are adding to the intrinsic strength, and we are adding something which is in proportion to the distance between the intrinsic strength and the maximum possible strength, which is 1. And there's also a function of the difference between the strength of the attackers and the supporter. This just to give you an intuition about what this, what semantics could be. And again, to illustrate what properties could be in this particular case, dialectical monotonicity is an interesting property. It basically boils down to saying that attacks decrease dialectical strength and supports increase dialectical strength. So if we had only the supporter here and no attacker, then we would have had a higher strength for A1, but adding the attack would have decreased it, just to give you an intuition. Okay, so that's a very quick overview of a form of argumentation. Probably, if you have heard about argumentation at all, you heard about abstract argumentation, whereby there are only attacks and no supports. And rather than computing dialectical strength as a number, one computes status of argument as being accepted or not, or accepted, rejected, and undecided. And these are kind of extension-based or labeling-based semantics, which are alternatives. All of these forms of computational argumentations can be used to provide explainable AI solutions. And overall, they can be, there are actually quite a few such solutions these days. We refer to this overall area of working explainable AI as argumentative explainable AI. So in a nutshell, this is about putting together argumentation frameworks and models that need explaining. Models or data, actually. So you may have a system possibly built from data, possibly just have the data, possibly the system is black box, plus possibly it is interpretable. That doesn't really matter. The vision is that you want to be able to explain the outputs of this system to a user. And in order to do that, you provide an abstraction of the model, of the system, of the data, of the output at hand as an argumentative, as an argumentation framework, which could be any of the ones available. And then you use this abstraction for building argumentative explanations. The argumentative framework provides some kind of interpretable counterpart of the system, which is not the explanation. The explanation needs to be extracted from the argumentation framework itself. And the idea in most approaches that take this view is that the argumentative explanation should be interactive, should allow for an exchange of opinions with users. So we have recently written a survey on the several approaches in this spectrum, and we have classified approaches as of three different types. There are approaches that are intrinsically argumentative, so they are defined for models that are natively using computational argumentation, so the systems are argumentative, and then it's easier to build an abstractions. Then basically they come with an abstraction, so the challenge is just to build argumentative explanations. But you can also have systems that are post hoc argumentative, so you start from anything which is non-argumentative, and then you build an abstraction as an afterthought, which is using an argumentation framework. And this abstraction can be a complete in one-to-one correspondence or approximate. And again, you build argumentative explanations from this abstraction. What's interesting here is that the intrinsic approaches will need to choose a semantics because that's part of their definitions. But in the case of the post hoc methods where an existing system exists, we cannot choose the semantics whichever way we want. We want to make sure that we are building a counterpart of an existing model. So we need to find the semantics in the model itself. So the semantics is inherited. So the challenge is to build the abstraction so that the semantics has desirable properties for the abstraction. So I'm going to try and make this a little bit more concrete with a couple of examples. And I'm starting with an example whereby we start with a non-argumentative model, so the second category, and we go for an approximation. And that's the explanation of a black box model for text classification, which uses a convolutional neural network, admittedly a simple one. The convolutional neural network, despite being simple, because it had just one hidden layer, is nonetheless opaque. And given an input text, it would return a class. For example, given this bit of text in input, it may say that this is about business. It's classified as a business text. And then again, we want to find out why this is so, how the machine came about that output. So here, what we're interested in is not necessarily a shallow explanation, which just tells you, as heat maps do, which bits of the inputs are responsible for the output. We're really interested in finding out how the model, the convolutional kind of neural network thinks in order to provide that output in a way that is lending itself to interactions, exploration by interactions by the users. So the way we go about this is we build an approximation of the network itself. This is for the output computing for this kind of input. So this is a local explanation. And the argumentation abstraction is a bipolar one, where plus green edges are support and red minus edges are attacks. Arguments are of three kinds. The input words in the text provide arguments. And as you can see, they are repeated. So they may need to be copied because they may activate different filters in the convolutional layers. And these filters themselves are arguments in the debate. And these arguments are what support or attack the prediction, which is, in this case, business, and that's also an argument. So input words, filters, and output class are arguments in the argumentation framework. The size of the arguments corresponds, in this particular case, in which we're approximating the original neural network, corresponded to the LRP values of words or of the filters, or the confidence in the prediction probability of business in this particular case. And this is basically the argumentation framework. And we already have the semantics when we start constructing it. That's LRP, but we want to see as a gradual semantics. So the higher the size of the argument, the higher this kind of LRP value. And we extract the argumentation framework in such a way that it has these desirable properties that attacks increase strength, decrease strength, and supports increased strength that I mentioned to you before. So here we start from the semantics, and we are driven by the properties we want the semantics to exhibit to construct the argumentation framework. Okay, this is just an abstraction of the original framework. It's not an explanation yet. And per se, it would be as black box to a user as the original model, because the user is unlikely to understand anything about argumentation. And also, the filters mean nothing at all to a user. So we need to do a little bit more work to obtain an explanation. And what we went for is using word clouds as ways to interpret the filters. And we obtained the word clouds by collecting all the examples that activated those filters and then building word clouds from those examples. Here I'm talking about the training examples. So and this can be done, of course, before any input is given, a kind of compile time, and then we kind of have a representation of which filters attack and which filters support the output, and then a combined representation, which is a kind of heat map, if you like, of the activations of the kind of the way the input words activate the various filters for this specific input. What's interesting is that we can support interactivity with this kind of explanation. A user, for example, could click on one of the filters, such as the rightmost here. This, I think, corresponds to filter 5 in the argumentation graph. And then one can see that this is attacking the prediction, the classification of business, and is supported by these 3 words in the input. And you can see why this is the case, and in a sense makes sense of what the machine, the model, is doing, and see that the model makes sense. It's actually, the model is actually thinking that these 3 words which are really about military more than business, are indeed supporting this filter, which again is not about business, but is more about military, if you like. And this is, intuitively, correctly attacking the prediction. So the interactivity in this particular case is obtained by just clicking on these filters and provide information about the mechanism, the underlying mechanism, in addition to provide shallow information about which bits of the inputs are responsible for that output. So we call this kind of explanation deep, and it's or mechanistic because it's about the actual mechanism itself. We can use this kind of strategy, building argumentative explanations, also from, rather than from the mechanism itself, from further abstractions of the models. For example, causal abstractions. So we are looking at this in training neural models that are aligned with human knowledge as well, and then use the kind of causal graphs extracted from these models to provide argumentative explanations that actually human users can also interact with by saying, oh, the model, there is something wrong with the model. Really, you shouldn't have this kind of causal relationship, or you should. So we are also doing work in this spectrum. I'm happy to take questions on these later on, but I don't have much time to go into details. However, I would like to say that this is again about building argumentative abstractions, but they are about building argumentative abstractions from causal abstractions of a model, and doing something more than the causal model is doing, because a causal model only tells you that there is one type of influence. No, there is one influence which has a causal nature from one variable to another, whereas the argumentation framework is telling you what type of influence it is, whether it's positive or negative. So there is additional information that one can extract from a causal model from the causal graph. And that's argumentative and can be used for interactive explanations. And then the other interesting aspect is that one can actually, from these argumentative abstractions, one can extract other forms of interactive explanation, for example, conversational ones. And in this particular work, we looked at kind of well-defined, controlled conversations which are driven by templates. We extracted a kind of argumentative abstractions from reviews on movies taken from Rotten Tomatoes, where critics put their opinions on movies. And then we use the abstraction from the reviews, which are argumentation frameworks, as our source of recommendations. This is an example where we define a model as intrinsically argumentative. And in particular, we use an ontology for arranging opinions identified in the reviews in an argumentative structure. In particular, we would say that the movie is going to be influenced by, the goodness of a movie is influenced by acting, directing, and writing, and the acting is influencing by performances of kind of specific actors. By looking at reviews, one can collect votes from various critics and determine a kind of intrinsic strength of various various aspects of the problem, as in this case, and then apply a conventional argumentation semantics to determine the dialectical strength. Doing that would lead, in this case, to maybe a high strength for a specific movie. Independent of how this graph is obtained, what's important here, for the sake of this presentation, is the fact that one can build naturally conversations with users, leveraging upon these graphs. For example, a user may ask, why was this movie, The Post, say, highly rated? Because 0.85 is quite high. This is within a 0-1 range again. And then the system may look at the argument corresponding to the movie, which is this M, and then identify the strongest attackers and supporters and use those to reply. This movie was highly rated because the acting was great, although the writing was poor. And this is because of an attack. So the choice of including also attackers is arbitrary. One can decide to just have supporters. One can decide to have multiple supporters and multiple attackers. So there is a whole variety for developing templates here. And then the user can further inquire and say, why was the acting considered to be great? I want to know more. The system can then look at the strongest supporter. There is no attacker, and come out with this reply, for example. And if further inquired from the user, the system can dig down into the reviews from which these numbers were computed in order to provide a fully engaging conversation. Can I ask how much more time I have?
You have 15 minutes.
15 minutes, including questions?
Including questions, yeah.
Right, so let me go for another 5 minutes, and then I'll take questions. We also look at settings where, which are maybe more of interest to the planning community. We have looked at explaining decision-making, very simple forms for the moment. We have decision sets, goals that these decisions meet, and then we have criteria, for example, with dominance that can be applied. Without going into details, let me just tell you that we are interested in explaining why a certain decision come out to be weakly dominant in this, according to this notion, and why not. We define lean or shallow explanations for these, but we also provide mechanistic argumentative explanations that leverage on what we call dispute trees for argumentative counterparts of these notions of dominance that lend themselves to some kind of interactive view of the decision-making process. This is something we haven't yet published. It is submitted, it's on archive, and again, I'll be happy to answer questions if there are any. I would like just to give you an idea of the range of settings within which we can apply these techniques, going from machine learning models to recommended systems to decision-making tools. We study properties of these argumentative explanations, ranging from cognitive tractability, computational tractability, and fidelity. These are kind of important aspects when you want to develop explainable solutions that are really matching the model and are doable in real time, and that the user can understand. And we also look at existence and uniqueness, which are rarely satisfied by feature attribution or counterfactual explanations in the literature, for example. And finally, we look at coherence of explanation, that the explanation makes sense by being, for example, consistent. So these are just examples of the kind of properties we're working on, and there are several others that are of interest. And then, of course, we are interested in looking at the amenability of explanation to humans. This requires doing experiments with humans, and we have, for example, conducted experiments on 3 alternative formats for explanations for recommended systems that are built from the argumentative abstractions. And we have compared tabular explanations that may be drawn from these argumentative abstractions, textual explanations, kind of summaries of what the recommendation's rationale is, and also we looked at conversational explanations. And we saw which of these actually allowed users to better understand how the recommended system worked, And here we are showing the kind of correct answers before showing explanations and after showing explanations, indicating that no matter which format of explanation, they are helpful in understanding how the system works. So they are kind of cognitively tractable windows over the underlying models. But the kind of indications about which format of explanations, and in particular, whether interactive explanations are better appreciated by users is inconclusive. As you can see, the interactive form of explanation, which is IE3 here, is not the most preferred one. So this kind of experiments provides information and needs to inform the way in which we develop explainable AI solutions. So I managed to get to the conclusions. I hope I have convinced you that computational argumentation can empower various forms of explainable AI, ranging from shallow to deep explanations for a variety of settings. And I am looking with colleagues at applications of these ideas in finance, sponsored, funded by JP Morgan and the Royal Academy of Engineering in the UK, and in healthcare and law, funded by the ERC. We have a seminar series that I hope some of you will be interested in attending, and I'm currently involved in organizing 2 relevant events. One is another Explainable AI workshop for KR, and the other one is the Computational Argumentation conference. There is a lot of future work to be done, and I'm just putting the list here and taking any questions. Thanks for your attention.
Thank you, Francesca, for the great talk. Yeah, so if anyone has any questions, please you can use the reaction to raise your hand, or you can just turn your camera on. We have a question from Sarah.
Hi, this is just more of a clarification. So going back to the book on Enigma of Reason, right? Did I get that right? I'm not sure. But you were using the term reason to say, okay, the reasons are how people justify things and stuff like that. Was it being used in like a technical sense, or was it more like the English word reason? Or is it like is there a causal semantics to it?
Are you referring, sorry, I can hear you partially. So are you referring to the interactionist view of reason?
Yes.
Right.
So the question was more about the term reason. Was it that being used in like a technical sense, or is it just the English word?
I think that this is a kind of popular psychology book, I would say.
Okay.
So the way that Mercier and Weber use reasons is more as a kind of rationale for what one does, the way I understand it at least.
Okay, so it doesn't have to be like a causal thing or anything, like this particular, there's no causal relationship between.
Not necessarily. Okay. I don't remember whether they bring up the causality aspect, but of course, if you have, I would say that a causal connection would be, a causal influence would definitely be a good candidate for a reason, at least in our explainable AI setting. And if you look at what I kind of very briefly talked about here, is the fact that you can indeed use a causal relation between I don't know, education, whatever it is, and income, which is the classification. This causal relation can be seen as a reason for why the prediction was that the income is greater than 50K. So I think you are perfectly right in making that inference.
Thank you.
I don't see any other. I have a question in the meantime, though. So when explaining the black box models, you had, I've lost the share the screen.
Yes,
Oh,
sorry,
that's it, that's it.
I unshare because I couldn't see you, but I can.
Oh,
I can
no worries.
Go on. I'll share.
So when explaining the black box models, you have the recommender systems and working on, you know, what looks like some word embeddings types of things. But what happens if the input is uninterpretable? What happens if there's no symbolic knowledge with the input? So for example, maybe just raw pixel data or something like that. How would you be able to kind of attribute anything to that?
I would actually say that those settings, in my mind, are possibly simpler than others. Believe it or not, we have more problems with tabular data than we have with unstructured data such as text and images. In the case of images, one can, for example, identify regions, or one can. What we do quite a bit is kind of make sure that we kind of interpret latent features in a way that is aligned with human features. So, for example, we could have color as a human understandable feature that then can be aligned with a certain, I don't know, filter in a convolutional neural network. What is really tricky is tabular data, because suppose you have a very deep setting and you have, built from tabular data, then how do you kind of show a filter or a set of neurons somewhere in one hidden layer to a user? So each type of data, of course, comes with its own challenges. And one great aspect, one important aspect of this vision, as I told you, is somewhat making sure that the bits of the argumentation framework we extract are interpretable. Because if they're not interpretable, then the argumentation infrastructure will only provide so much information.
Okay, yeah, great. That's very surprising, actually. It's yeah, but I can see with very large tabular data that could be the case. Do we have any other questions from anybody here? If not, I have another question. Let me see. So another question I had, and this is maybe a tricky one to answer, but because this is an issue when it comes to explaining black box models just in general, but without a ground truth, how do you kind of evaluate the explanations that you have bar user studies, with extracting that data from the black box model? How do we then kind of know that it is the correct explanation for the output, as it were?
Yeah, so this is a very good question, and there are many facets to this to this question. So the first important thing is that how are we sure that we are not cheating the user by providing an explanation which is making sense to the user, but is really not faithful to the model? In a sense, what we want to do is build an explanation that matches the model. That's why faithfulness is so important in this particular case. So we definitely need to have that, that faithfulness. And maybe a faithful explanation will show that the model is rubbish. And really, the explanation should be a way to allow the user to potentially debug the model if one sees that, the faithful explanation is not intuitive. So we actually have used and are using explanations to build the way I've indicated to support the biasing of models or elimination of artifacts in models, etc. So that's very, very important. But even assuming that we have a faithful model, because a faithful explanation, that still one needs, your question still raises issues, because that explanation needs to be understandable by the user. Because the most faithful explanation to a model is the model, but it's not going to be useful to any user. So then that's why we consider something like cognitive tractability. So is the user able to process? I mean, we, for example, could look at, I don't know, the size. Is the explanation linear in the size of the inputs? that's a good indication that it may be cognitively tractable. So definitely there is that other aspect as well, what it is. But then there is also another aspect which we assess with human experiments, and it is, what do you want the explanation to do? If you want to debug the system, then you want to make sure that the explanation allows the user to clearly understand what the system is doing. But if you are trying to, tell a layperson why they didn't get a mortgage, maybe you don't really have an issue with debugging. You just want to make sure that the user is empowered to understand, what it is about their case, their particular circumstances that led to their result. Maybe a counterfactual explanation, a shallow one, is the best thing to do. So there is definitely a challenge with understanding how to customize explanation, understanding what the explanations are for, and design explanations that can be provably demonstrated to meet those criteria.
Yeah.
And that per se, it's an art and craft.
Yeah, I mean, so the other kind of follow-up question to that is that, for example, you mentioned SHAP and LIME and these types of ways to explain, and there's the issue where you might not have robustness across different input and outputs for SHAP values, for example. Very similar results might give different key features as the result. Have you tested to see if there's sort of robustness in this approach as well, or do you have the same thing where you can have?
Yes, you're perfectly right. So I would say that LIME and SHAP, any method that is based on perturbations and random choices will not be stable, we could say, or consistent. So you may ask actually twice to explain the same input to output pair and get completely different explanations. Or you could, as you were saying, ask for two similar inputs, output pair, to be explained and get different explanations. So what we are trying to do is methods which are reliant upon perturbations. So they're non-reliant upon randomization, and therefore prove robustness and of the kind you were mentioning. But these are of course challenges, and the definition itself of what robustness means, or stability means, is something interesting. So we are with a colleague and PhD student, Guilherme Paulino Passos. We have a paper on a kind of interactive theory of explanation that we will present at the Explainable AI workshop at XAIP, and also at the XLOKR explainability workshop at KR, a variant of. So I'll be happy to share the camera ready with anybody interested once we have it, because it tries to address precisely your concerns, Benjamin.
Okay, great. Okay, I mean, I think we could have one more question. If I don't think anybody else is raising their hand, so I think we're 2 minutes over as well. So I think we'll go into the break now. Thank you again very much for your time, Francesca. And Francesca is going to stick around and join us on the panel, which will be in half an hour as well. So that will be great. Yeah, thank you again for that. Thank you. We will break again. We will break until 4:30, which is 4:30 my time, but whatever time that is for you, 4:30. Okay, great. Thank you.
Okay, I believe all our panelists are here. So it's now it's time for welcome back, of course, everyone. So it's time for our long-awaited panel. And with us, we have Professor Bertram Malle, who joined us from Brown University. We have Professor Francesca Toni, who just gave a talk previously. We also have Professor Mark Riddle, who gave a great talk yesterday. And also we have Dr. Tathagara Chakraborty from IBM. So to preface things a little bit,
So we can say that in explainable AI, there's a growing agreement, more or less, that explanations can be best modeled as a conversation between the system and the user, right? However, most of the work, and particularly in the planning community, tend to focus on one-shot explanation methods, basically on a single interaction of the overall interaction between a system and a user. And many of these explanation generation methods generate responses to specific queries. As many of you may know, for example, why this particular plan, or why this action or this other action, and so on. And while this has led to the development of several useful methods and tools, we're still far away from modeling and supporting the entire explanatory dialogue. Now, how can we get a step closer to achieving explanatory dialogues in our systems? What are the research challenges and opportunities related to modeling, implementing, and evaluating explanatory dialogues? So the aim of this panel is to motivate us to look at this interesting problem of supporting an overall explanatory dialogue. So what we'll do first is we're going to start with each panelist giving about a 5-minute remark on their views on this topic, and then we're going to open up the floor to questions and hopefully more interactions and discussions between us. Okay, let's get started. Let's see. Tathagat, I'm going to go first. Give us your views on that topic.
Yeah, sure. Let me share my screen.
All right.
All right. You can see, right?
Yeah, yeah.
Okay. Yeah, I mean, so first of all, thank you for inviting me to the panel. The explanations and dialogue are both very interesting topics by themselves. Although I'm not sure it's interesting when you put them together, I have my reservations. So I'm going to take a negative view on this, and hopefully we can have some interesting discussion on that. So first of all, I would like to start with a brief thought experiment in terms of how many of you have asked Siri, why did you not understand that? So as you know, if you're using virtual assistants, one of the most common things to hear is, sorry, I didn't understand that. And partly because dialogue agents are very, very brittle as of today. I know the scope of the question for the panel is not particularly to explain dialogue itself. But the reason I bring this up is for two reasons. So given that dialogue itself is a hard problem, I don't think there is any reason to believe that explanations using dialogue is going to be any easier. It's at least as hard. And to the extent that explanations as is today is supposed to make things more usable, piggybacking on an already brittle system seems like a bad idea. But also, secondly, as we have talked about before, on in any talk, you will hear about end users and developers and different kind of users that need different kind of explanations. It turns out that the people who are interacting with systems in dialogue are not the same people who are asking for explanations. So in this case, you have a dialogue system where users rarely ask explanation questions. At the end of the day, they want to get things done. So when we talk about end users and explanations, it is the case that different people want different kind of explanations, but it's also the case that different people use different kind of interfaces. And the people who are using interfaces that deal with dialogue maybe are not the target for at least a vast majority of explanation techniques that's in literature. Of course, traditionally, the number of explanation techniques have been much more focused on the end user, on the developer instead. And it has shifted a bit over time. I think Mark also mentioned this in his talk yesterday. There's also the third kind of user that we don't talk about, which is the person selling these products. So if the moment something becomes explainable, it's more sellable in the sense that it's all sorts of compliant. and kind of similar to how the seller doesn't care whether the explanations are useful or not. The developer persona is the only one that really cares in terms of understanding the internals of the system. The end user also doesn't care either. And to that end, I want to take a position that that really what we want is explanations for the person making the system, but different sort of interaction where you know where the system is going for the end user, with the intent that these things must be actionable. And this is something also that Mark mentioned yesterday. Ultimately, we want these kind of interactions to be actionable, particularly as it relates to dialogue. You could think of this in the form of, for the end user, if they're talking to the system in multi-turns and they hit a position where they can't get what they want to do with the system, the predictability notion would be, what do you say instead? So if you look at conversation systems right now, if you get stuck, it will tell you maybe you could do these other things. I can do these other things to help you, or maybe you can rephrase your sentence in a different way. It's all about getting them out of the current spot to a position where they can get the job done. Whereas for the developer, they're looking at a space of possibilities. So when they're making the system, the point of explanation is to make sure that they understand what it does once it's deployed. And to the extent that the developer is an expert, you could say that explainability is sort of almost predictability, because they have knowledge to interpret that explanation into an actionable form, which may not be the case if you have an inexpert developer, right? So there is a mixture. There are a lot of applications now where we want to have inexpert developers who can build things using AI. In that case, again, just having an explanation is just not enough. So in terms of seeing this in action, we have worked on some conversational systems at IBM that have explanations built into them. So this was an example in a banking scenario that we were kind of explaining what the underlying business process is. The explanations is not really in terms of things that are going wrong or the dialogue itself. Because there was an underlying process here, there were things to explain. The interesting part is that the end user always doesn't know if something is going wrong. So it's kind of tricky to merge in the explanation of the process versus the system itself. I don't want to go into the details of this, but just the developer view is that once you're building these systems, it turns out that this is an example of building a dialogue system itself. What you want to give the user is a view of the possibilities, not just individual instances. So from the AI point of view, what you observe as the end user is an instance of a policy at most, the behavior of the system, whereas you are, as a developer, you are dealing with the entire policy. And so you as a predictable nature of the system should be able to tell the user what to do to make it better. And we have worked on combined systems where we kind of have multiple modes of interaction. So in a sense, you could merge dialogue and interface and so on. And that kind of gets you out of dealing with explanations and dialogue together. So I won't take more time. Just to summarize, I think you can't differentiate the mode of interaction and explanations. It's very likely that the system would be working in the same interface for explanations as it's working for the rest of its capabilities. And given that dialogue itself is very hard to model, I don't expect it to be any easier or to become better with explanations also in dialogue. And more importantly, the users who are interfacing in dialogue with the system are not the users who are asking for explanations. And if they do, then we want to have a notion of predictability, not explanations. So I'll stop here and then hand over to the rest of the panels.
That's great. Thank you. We're going to get back to that. All right, our next panelist, who wants to give us their views? Yeah, Professor Toni, yeah, you.
Yes, not a problem. So I have a different view, and I guess that's why we have a panel, because we want to disagree. So I can kind of share quickly some slides. So let's start from the first. So the question is about whether I agree that explanation should be modeled as an iterative dialogue, and are there situations where the current one-shot interaction paradigm suffices? I mean, to me, I guess in my own presentation focused fully on the fact that explanation needs to be interactive, and the dialogue is one way to support the interaction. But I don't believe that dialogue should necessarily be iterative and carry on unless and until the user wants that. And there are indeed, it is possible that in some situation the user would not want to engage in the dialogue. I have given you the example of the recommended system built from reviews from Rotten Tomatoes. The underlying argumentation framework guides the dialogue. It's unimportant now what it does, but it's the user prompts that trigger the system to provide information and engage in a dialogue. Should the user stop, then no further information would need to be required. So I think that we need to design interactive explanations, including using dialogue-based systems in such a way that they can be customized to the needs of users, and so that they do not overwhelm users with too much information. So that's my views. In a sense, it's yes, interaction, possibly iterative dialogue, possibly not. Concerning the second question, which is concerning the research challenges that arise when one considers the problem of explanatory dialogues, I think that one important challenge is that although in the experiments we have done with humans, it comes out that having explanations of some form helps understand the system, there was no clear evidence that the more interactive types are preferable to the one-shot ones. Here we consider three models: tabular, you just put all the information in a table, information that is relevant for the explanation, or textual as a summary, or conversational in a guided dialogue kind of way. And you can see that there was no obvious preference for the dynamic dialogue versus the static provision of information. So I think we need to be able to accommodate that possibility that dialogue is not what the user wants, and the main challenges amount to characterizing the situation, characterizing to me the cognitive abilities of the users, so the users at the receiving end of explanations. And then in terms of evaluating the third question, evaluating how effective the systems are, I think that we need to consider a bunch of properties, including cognitive tractability, not to mention the computational and fidelity, as well as other standard properties, but we also need to look at more dynamic properties, including coherence across different exchanges, different, if you like, interactions with the system. So it's kind of to summarize, I agree that there should be some interaction allowed, but there needs to be to disposition and kind of massaging things around the user. And there are definitely challenges in supporting interactions and challenges in supporting measured. So we've made some first steps, but there is a lot to do. So these are my thoughts.
Thank you, Professor Toni. Thank you very much. Okay, I'll go in order. I see the windows on the chat. Professor Riddle.
Okay, yeah, thank you very much. So I'm Mark Riddell. I'm a professor at Georgia Tech in the United States. And if you didn't see my talk yesterday, really, my colleagues and I have really kind of focused the last few years on something that we're now calling human-centered explainable AI, which is to say that I think we actually don't understand very well what happens when people engage with explanation systems, and we don't always understand the effects that they have on people and whether they find actionable and useful information out of explanations or get confused. And there's a million different research questions that I think could be asked and keep us all very, very busy for many, many years, in addition to also designing algorithms that support user needs. So, okay, I don't have slides, so I apologize. But I do have some kind of things that I think are worth kind of adding to the discussion here. I think it is important to distinguish between developers and end users, and I think also possibly salespeople. And I think the answer always depends as to whether interactive explanatory dialogue is useful or not. I'm going to say, like, with developers, I'm not sure the extra overhead of working through a dialogue system and a conversational system is always going to be beneficial. I think their developers are going to find the ways to get the information that they need to do their jobs, whether it's an explanation system or writing their own code or possibly dialogue as well. But I think my experience is that dialogue it will be seen as a distraction in many cases. For the end users, I think the answer is maybe. I can see the benefits. I think Francesca had a great kind of motivating example of a case where it could be used, but I don't think it's going to be uniformly and universally accepted as the right thing to do. And the reason I kind of decide that's kind of where my head is right now is because to me, it all kind of comes down to the user's mental model. Right. So why do users have require explanations or ask for explanations in the first place? It's because they don't understand a decision or a behavior that an AI has made. And that to me, that means there's a disconnect between what the user expected and what they got. That's not always the case, right? So sometimes they just get an answer and they don't even know they should ask a question. And so, it all comes down to what helps humans build better mental models of the systems they're using. And to me, we're talking about end users, people without technical backgrounds here. So their mental models are going to look very different than the ones that we have when we're talking about AI and machine learning. And ultimately, is the algorithm affording more actions, right? So coming back to the point of, do we even know we should ask a question or get involved into a dialogue with the system? Sometimes we have to know that we can do that, and we should question the system. And so, to me, whatever gets the user there is the right answer, whether it's a dialogue or not, right? So I talked yesterday about probing, right? So, sometimes we need to challenge the algorithm to understand it, to make sure that we got the correct answer. Do we allow people to do the probes, which is to ask questions in a dialogue capacity? Or should we automate those probes? Should we basically take on the role of forcing the user to reflect on the answers? Because, well, here's my worry, right? So we're all trained scientists, we're all trained to be skeptical and to challenge and ask why, but most people are not, right? And there's a huge issue with systems that don't explain themselves, that don't want to be explained because they've given the answer to the user that they want the user to have, right? It's not, what we're basically saying is users should feel free to challenge us. I like to think about this as like, should we treat AI as con men? right? What do you do with a con man, right? The more you challenge the con man, the more you're going to discover the flaws in their arguments, right? So, but it's not our innate capacity, and it's not our innate kind of human kind of modality to always do that. So what do we do to help them? We can start a conversation, and maybe that goes further, right? So, you know, I used to think that creating rapport with humans was going to be one of the important things that explanations do. Now I worry about persuasion. Can dialogues create a sense of greater intelligence or greater authority than the system should actually have, right? So the things I've seen is really easy to convince people that AI is smarter than it is. So if the AI seems smarter than it is, do we accept its answers without judgment? Do dialogue basically come back and hurt us in the same way that in this last week, people have been asking whether Google chatbots are sentient? Sorry, I had to bring that up. If you haven't heard about this, don't Google it. Okay, so those are kind of like the dimensions I think that we need to think about when we decide whether whether the design of our explanation system should involve dialogue, interactive dialogue or not. I'm for it when it helps, and I'm against it when it doesn't help. And I don't think we always know when. What are the challenges? I mean, so the challenges are that different levels of abstraction. So I think one of the reasons why we might want dialogue is you can start at a high level of abstraction, maybe a rationale. And then if that is insufficient to help people build the mental models that we need them to build, we need to go deeper. The challenge is that the high level rationale generation might look different than the meso level, mid-level explainer, which might be a completely different technology that goes in well into the weeds of the neural network or the reinforcement learner, whatever the agent is, right? Since we have to build 5 or 6 different explainers who come in at the right times. And if they come in at the wrong times, then things get confusing. That's just a challenge. Something to think about. There were some great talks yesterday about explanation systems that could actually go up and down the level of hierarchies. I like that a lot. And then the other challenges are the standard challenges in dialogue. So what is the user trying to achieve in the dialogue? What is their intent? What is their goal? And if we understand that goal, can we tune the dialogue and the explanations better? That's a plus if we can solve that problem. How do we ensure that we're tracking context? So we're actually not just like sequencing up a bunch of one-shot explanations and calling it a dialogue, but to use old information to inform new explanations. I think we don't know how to do that at all. I think we barely know how to do dialogue with context. And I think generally, like, an AI system should have to figure out, why was the first interaction, why was the first explanation insufficient? What is it failing to achieve with the first answer? Because if it doesn't know that, it's not going to know how to follow up. And I think those are some of the challenges from a technical standpoint that we'll face. And then finally, guidelines for effective evaluation. I think, again, it comes down to my bottom lines. Does the user's mental model change in a positive way? Do they have a better understanding of what the system's capabilities are? Has the number of actions, the responses, what they can do with the answers from the AI system, has it expanded? Have we given them more capability to remediate their situation or to take proactive steps to improve their situation? I think those are the things we should evaluate, whether it's interactive or not. And then another one I like is, I think, will people want to interact with the system again? So, right. Okay, that was a lot without slides. So hopefully that made sense. I'll hand it over to our last panelist now.
It absolutely did. Thank you very much. And last but not least, Professor Malle.
Right. Well, thank you for inviting me. Let me share my screen. I have a few slides. I have to say, the discussion about explanations always reminds me of Yogi Berra saying that predictions are hard, especially about the future. And we could vary that to say explanations are hard, especially about or by artificial agents. So I think it's very clear to everybody this is a damn hard problem, one of many. So I just want to maybe give a little bit of orientation here. that in order to understand or decide whether explanations as dialogue are necessary, I think it is important to realize that explanation is relational. And what I mean by that is that there is an explainer, an audience, and something to be explained, a behavior, an event. And it was nicely already said by the previous panelists that the audience can vary. It can be the user, can be the developer, can be the salesperson, the government agency, can be all kinds of audiences. The explanations will differ. So we always have to keep in mind that even before there's a whole dialogue, that even very first statement proposition of an explanation is E explains B something to A. And I think that pretty much everybody's in agreement about that. Now, there is, this might be a little silly, but there's an important difference between what people call explainability and explaining ability. Explainability is just whether somebody, some explainer, can explain a machine's behavior to some audience. And that behavior could be quite trivial, could be a detection criterion, could be the order of doing certain things, or it can be something much more complex. So somebody can explain it. And this is a pretty low bar, to be honest, because an explainer, like a developer, can offer some information. And then the question is whether the audience can do anything with this at all. But the system is still explainable. It doesn't really do a whole lot. Now, what I'm particularly interested in, because I'm interested in social robots as a sort of a class of AI or AI agents, is whether they are able to explain, whether they're explaining able. And it means the machine itself has to explain its own behavior to an audience. And again, that could be the developer, it could be just showing its code and say, this is what I did. You figure out why that was wrong. Or it can actually give an explanation to a user why it did certain things or did not do certain things. So here we have the same situation, but in this case, the explainer and the machine are the same agent, but the machine behavior is still a third thing, and the audience is still very distinct. But it is a much higher bar, because now the agent has to have some form of awareness. It's all very difficult. Now, in order to figure out whether dialogue is necessary, I do want to distinguish between different degrees of dialogue and different degrees of explaining ability. The minimal is just one that the machine can give an explanation to an audience that actually answers the why question that the audience has, close their understanding gap, as it's sometimes called in empirical, but also philosophical explanation literature. And that means there is some piece of knowledge that's missing, and it doesn't always have to be a why question. It can be a how question, as we saw in one of the earlier slides. It can be just a that question. But the minimal thing is to recognize what that question is, what that gap is. And that's not even that easy, because people don't often completely clarify and explicitly state what it is that they're missing. They sometimes don't even know exactly what they're missing. And there's a great philosophical contribution by Sylvan Bromberger, who says that explanations have to have a model of what the possible answers to the questions might be. And then you pick from the possible answers. And it means you need to really understand the question in the first place. The next level would be an anticipatory explanation, where the system recognizes the audience's gap of understanding in advance. But of course, there needs to be a gap of understanding. Systems that constantly explain themselves or are very verbose are going to be very annoying. So the system has to anticipate, or the user has to be the one that initiates a request for explanation. Explanations are often not needed. As it was stated, that sometimes people just go along and act, and they don't necessarily, they may have a confusion, but they don't necessarily ask for an explanation, because it might reveal itself and then they can keep going. Audience design, as it's called in some literature, is when the explanation as a piece of communication takes into account something about the audience's knowledge. What they already know cannot be the gap in understanding. Contrast cases, many people have worked on that. Why did the system do this rather than that? And that's a critical issue, right? Your gap in understanding isn't why did the system do this compared to 7 million other things, but rather there's a particular expectation. And why was that not met and instead something else. And that sometimes can be a very simple single answer. So recognizing that is key, but it's difficult. It needs to have a model of the user's knowledge and the specific contrasts that the user has in mind, or the audience has in mind. And then continued dialogue is really the fourth level. And this is what people have called drill down here. So you are able to respond to follow-up questions, which means you have to understand how the follow-up question relates to the previous assumptions, the clarifications that might reveal the audience's misunderstanding or the system's own false assumptions and inferences. So to do all that is not just having a good dialogue system, but having a constantly updated model of the user, of the system itself. And I don't think we can or should go there anytime soon. I'm of the simple-minded belief that if the system can't give a satisfactory answer, it needs to escalate to a service center or a supervisor or something else, because otherwise the dialogue might become more and more frustrating. The user will, or the audience will expect the answer at least the second time around. And if it's not there, they'll just give up. So I think it might be sometimes better to say, I'm sorry, I cannot give this answer. And Siri does that, but then there's nothing. Siri doesn't offer what to do instead. And I think sometimes, especially with social robots, the way we think of it is that there always needs to be somebody on call, a supervisor, or maybe even a customer service number, so that if it's really important, there could be a follow-up that the system may not provide, but somebody needs to provide. So these are levels of difficulty where I think eventually dialogue could be useful, but often it isn't useful. And it's sometimes the minimal closing of the knowledge gap is all that we need. But that's hard enough to understand that gap in understanding. Right, so those are just my framework thoughts. I'm not going into some of the technical issues because that's not my expertise, but obviously the things that I lay out here provide some constraints on what the technical approaches need to address, if that's important in the particular agent's use and function and context.
Thank you. Thank you very much. Very, very interesting. All right, now let's open it up to questions. I think I believe we have a lot of things to talk about here. So if anyone has any question, can raise their hand or speak up or post in the chat. I think Sylvia, you had a question. You can, if you wanted to. Otherwise, yes. I can. Okay.
But if you want to go.
No. Please. Yeah.
Okay. So thanks a lot to all for the discussion. It was interesting to listen to your different point of view on the question. Starting from Tagata, what I wanted to add is that yes, it's dependent by the end user and by the type of user that you have in mind when you develop the explanation. But I think this was raised by others after you. It also depends a lot by the goal of the explanation and by the goal of the task that maybe a human has to do with the agent. So I think when we have, for example, a situation where an agent has to collaborate with an AI system, then this mutual modeling and this dialogue and this fact of having an explanation is not just for predictability. It's not just for predicting what the agent is going to do. It's also to shape other aspects of the collaboration between the two. And another example in which, for example, predictability, I think doesn't hold. It's also if you have a learning scenario, for example, and you want the human to learn something from the explanation, then this doesn't hold. Predicting, it's not enough. Understanding something more about the functioning of the system, because, for example, I don't know, there is a decision from a diagnosis. The typical example is there is a system that provides you a recommendation for a diagnosis and says, okay, this is a tumor, and you want to know why, but you also want, suppose that person who is looking to the diagnosis also wants to learn something about the diagnosis itself. and want to learn something more about the tumor itself, the explanation should be something more than just predicting what the machine is going to do, right?
Yeah, so I should clarify that by predictability, I didn't mean what the system is predicting, what the system is going to do in future. It is about, if I'm not getting what I want from the system, how do I change how I'm using it to get what I want? So from, let's say, as a simplest classification point of view, you could say that if I don't get the correct class with the current input, how do I change the input to get to the correct class? And what that means from a conversational perspective is, how do I rephrase my utterance? And the reason it's important is because once you deploy a system, so the life cycle of a system, the deployment life cycle is so that the system doesn't change in short cycles. Once you have put the system out, yes, it can adapt to the user in limited circumstances, but the model of the system is not going to change significantly over small time cycles. And so if the system is supposed to be usable in that small time cycle, then the user has to know how to use it and how to change their behavior to get what they want out of it. Ultimately, whatever didn't work may start working in longer timescales when the next version of the interface comes up. But between that time and the user is trying to use it for the first time, you don't get another chance at making the thing useful. Ultimately, if you say something, let's say the Siri example, if you say something to Siri, didn't understand what it said, you want the system to continue using it. You want the user to understand what to say instead to get what they want, and not wait for the next release of Siri 2 years down the line. And so the predictability point was to say that the task in those situations is not that we want to explain why Siri couldn't understand. We want to say, how can you say your things differently in the short term to get your job done? And partly the interaction question is sort of tied to the system itself. Like eventually, you don't want to build a system that explains itself in a completely different interface. Like, so if you build a conversational system and you ask it for an explanation, then there are very few systems that work across multiple modes. Right? You certainly don't take them to, here is a UI where I will explain my behavior. And when you talk to me in conversation, and vice versa. Right? If you're in a UI system and suddenly you start asking it, you want to understand how it's working, suddenly you have to go into dialogue. That's very hard to build. So whether we want to do explanations in dialogue is very much tied to whether we want to dialogue based on what application you have. And as was mentioned, like developers don't build systems in dialogues. So if we are saying that we want to explain in dialogue, we are constrained to users who are using things in dialogue. And the scope of explanations in those cases is much more limited. But also, it's not clear that most of those people actually want explanations. They want to use the system. And telling them why things are as they are is a less useful thing to do than to tell them how to use it better in the time frame before the next version comes out. So that's what I meant by predictability, not predicting the system's behavior, but predicting how can I change my own inputs to get the outputs I want.
I see. So it's more like an explanation of how you should use the system than how the system is working, like what are the inner working of the system, right?
Because imagine in the Siri case, if Siri told you why it didn't understand what it does, that didn't help anybody because it still can't do what you asked.
Can I chime in here for a moment? I agree that this can be useful, but it really is a different task or challenge than explanation. And maybe what you're saying is that we shouldn't even worry about explanation because this is completely out of reach. We should get the first thing done, which is a form of troubleshooting, right? It's basically saying, well, if you can't get it this way, try these buttons, try these things, try this option, try this pull down menu. And I think that's absolutely useful, but it is nowhere near anything like explanation. And it may often not be needed if the system that you're interacting with is pretty primitive. Like my computer, constantly, that's what I face, troubleshooting. I don't need it to explain itself. But any kind of interactive system that, again, going back to social robots roaming around in my physical space, or the agents that are supposed to accompany me during the day and give me advice, or to which I can delegate things, I may very much have a bunch of why questions, and then troubleshooting alone is not going to do it.
Yes, I should mention that my view is very much on the as is, right? Eventually, yes, when we get to systems that are sophisticated enough, then yes, of course. But currently, like, dialogue doesn't work by itself. So explaining why dialogue is even worse. Although we have systems that may trigger already needs for explanation. I mean, I remember we have sort of a mini self-driving car. It doesn't really self-drive, but it has a few auto functions. And we had passengers, and one of the passengers got really nervous because the car wouldn't slow down the way she expected or at the speed she expected, but rather, according to its algorithms, optimizing the speed. And if the car at a distance accelerates, then it wouldn't want to slow down too much. So she wanted an explanation. She asked me, but if I'm in the car for the first time and the car does something weird, I don't want to have just troubleshooting. I don't want to just say, okay, what else could I do for it to do what I want? No, I actually want something or somebody to give me an explanation. So that means even for these auto-serving systems, the need for explanation will arise. And I agree that we have to cover the first bases for sure, but the next ones arrive pretty quickly. Although in that case, I agree in principle, but it may not be dialogue with your car is maybe not the right way to interface in that case. So you have to go into a UX where you actually show what the car is seeing and that sort of stuff.
No, I wouldn't want to read a 600-page manual or go to customer service and be on the phone for half an hour. There might be a way of anticipating certain unusual behaviors by self-driving cars such that there are explanations ready to be offered that might cover at least 80% of the questions that users have. So I think even if that just can't, that could already be a lot better than nothing at all, or these useless error messages we get from most computers. Just nothing at all.
Can I jump in on that point? So, Dr. Malle, it seems like what you're hinting at is there are explanations for soothing and there are actionable explanations. So with your self-driving car, it may tell me that, oh, the reason I am trailing the forward car by such a long distance is because 90% of the time, if I'm within 10 feet, it's higher likelihood of a crash. I can't do anything with this information. Well, I might be able to force a change in behavior, but it might soothe me. How useful are soothing explanations? I mean, I would argue that most of the time when we demand an explanation, it's to try and change something about the system. Let me rephrase, like in bank loans, if my loan is rejected, a soothing explanation would be there, try again next year, the odds will improve. Whereas an actionable explanation might be, if you improve your credit score by another 10 points, your likelihood goes higher. I guess I'd like to push back on saying that soothing explanations may not even be useful. At least that's the way it seems to me.
Well, I think that what Sylvia said at the beginning of her contribution is really, it depends on the goal and the task. In some cases, absolutely. Whether it's soothing or not, it's at least filling my knowledge gap. I really don't understand why it did this, or why at this speed, or why in this order. And I really want to know, and the system can tell me, and that's it. That's literally the cognitive goal that I have. I don't need to act on it. In fact, I've already agreed to the system taking over my driving. There's not much actionable stuff. Whereas in other cases, absolutely, I want to change. I want it to be manipulable. I want to see what other paths I can get to the result that it didn't provide me the first time. All of that is absolutely true. It means there are very different demands we have on the system. Some of them are explanations, some of them are calming, some of them are actionable, some of them are troubleshooting. And I think calling all of that explainability is I think, one of the mistakes that has been made. Transparency is not the same as explainability. Comfort is not the same as transparency. Comfort is needed for trust. Now, we don't want to mislead people and constantly soothe them with inappropriate information, just make them feel better. But trust absolutely requires sometimes just having a feeling of understanding, or at least a feeling of rough understanding. And then I keep going. And I don't need the inner workings at that point. I don't need to change anything in my behavior. I just want to feel whether this is okay. I can still keep going. So I think it's both on the different circumstances.
Professor Nell, you raise your hand.
I'm muted. Yeah, I might be reiterating kind of what was just said, but I did start out with soothing. My research in explainability started out with what you're calling soothing explanations. And we saw, but it turned out there was actionability, because one action you always have is whether you stop using the system or not. You know, given two systems, would you continue to use a system that puts you at ease, that it's not making mistakes, or leaves you wondering as to what's going to happen to you? Right now, the challenge is inappropriate trust, right? So we can make you feel comfortable with the system by revealing information about how it's making decisions, even though you can't control those decisions. But we can also take it too far and make you feel really good about a system that is inherently unsafe for you. So there are balances, checks and balances that have to be drawn in here. But I think also fundamentally, like, we don't always understand what is going to be actionable to different users, and they're going to have different goals, right? So maybe for one person, actionability is deciding whether to use the system or not, to continue to use it. Another person might be, well, okay, I can actually, I can regrade my road. That'll make it drive slower. And that's what I wanted, right? So, I think sometimes it's up for the humans to figure out what they want to get out of that interaction. The challenge, of course, is how do we make sure that whatever are the explanations we produce is actually delivering for that. And I think since most of our panelists have come down on the side of not dialogue, I will force myself to be on pro dialogue here and say dialogue might be the way of zeroing in on the goal that the user has in order to then give the right explanation. And if that's the case, then I think that's a very powerful use for dialogue. What are you trying to do here? How help me help you, right? And once I figure that out, then I can give you the information you need, because otherwise I'm left guessing. Are you worried about the quality of the pavement? Are you worried about just feeling safe? Are you worried about, your own personal uncertainty? What are you trying to resolve? Where is your mental model versus where you want it to be?
If I may chip in, I kind of fully agree. And indeed, one of the things I did not stress, I fully agree with you, Mark. And one of the things I didn't actually stress is the fact that the dialogue is crucial for building a shared understanding of the problem. And in a sense, there is an element of understanding requirements, understanding preconceptions, understanding biases, understanding all sorts of information about the user that is the receiving end of the explanation in order to tailor the explanation to the user. Let me give you an example in the autonomous driving setting, but actually leveraging on a real driving, human driving setting and the need for explanation. I took a taxi recently to go to Stansted Airport in London. And these I took it from West London. Now, Stansted Airport is northeast of London. And it would be completely intuitive for a taxi driver to go west in order to go northeast. But I know that there are two paths, one being taking the North Circular Road, which is going west first and then going back east. So when I did ask the driver to verify whether he was going in the right direction, I asked him, "Are you going to the North Circular?" Because going west was counterintuitive, and he said yes. He told me a story about a driver that asked him previously, why are you going west? And was completely, untrusted. Wasn't really trusting the driver, so much so they called the boss of the driver and made a whole fuss. The mental model of this other passenger was completely different from mine. The other passenger did not have a mental model of the geography of the place and the options available to the taxi driver, and the conversation with the passenger unearthed that. So the kind of explanation provided to that kind of passenger was very different from the one the taxi driver provided to me. The one provided to me was that at this time of the day, because there are one can go faster on the North Circular, it's much faster to go this way. And this was not a satisfactory explanation for the other passenger. So the same way that humans dialogue with each other to understand how to explain, I don't see why machines shouldn't.
All right. Anybody wants to, any other questions? Or should I, oh, well, we have a hand, yeah. Mark?
So relating a bit to some of the discussions on, are we explaining to an end user or a developer, discussions like Mark brought up of, is there a risk of deceiving a user with dialogue explanations? I wonder what you all think of two possible goals for explainability. One is helping someone know how to use this system, explaining how they can use it better. And one is sort of openness and honesty about what the system is doing, how the system is functioning, and whether you think these are the same goals. So if we aim for one, we're also aiming for the other. Different goals, whether they overlap. And I think one thing that's interesting to me is I would be very suspicious that I think that openness and honesty is very important for AI safety and for AI that are actually doing good. But I think it's a lot easier to aim for AI that makes us a human know how to use it better and do that sort of explanation, and can fall into the trap of explaining things that make the human feel like there's a valid reason, when actually the AI is, in the case of bank loans, maybe the AI is just being racist, but the explanations are always, oh, you could increase your credit score in this way.
My answer is yes, they're totally different goals. And there's obviously plenty of room for being deceptive on the part of the designer. Whether the systems right now can be called deceptive themselves, I think is questionable, because that means there's a decision, there's a choice point. And right now, I don't think these choice points exist. But that doesn't mean they couldn't in the future. There might be trade-offs that systems have to make. The system might, for example, have some information that if it gives this answer, even though it would be the most transparent one, the user will be very upset. And that may not be one of the acceptable outcomes at this point. But once more, what's the alternative? The alternative is not to lie, but to escalate maybe to a different agent who can maybe handle the upsetness and the possible alternatives better. But I think right now we definitely have to worry about the designers of systems to give recommendations for the cheaper product when it actually isn't, but rather it's the product that the agent behind it, the manufacturer, tries to sell. So I absolutely agree. These are different goals, and we have to be worried about the different ways of manipulating the need for explainability, the need for transparency, the need for being soothed, the need for information, all of that makes users in principle vulnerable. If the ethics on the part of the designer isn't okay, then the system can't really do anything about it. It's just not in any way equipped to override those kinds of commands. And the user might definitely be in trouble at that point.
So the other day I brought up the notion of dark patterns. There are certain designs that are harder to turn into dark patterns than others. And again, I think of like the ability to probe or challenge a system, right? The more you can do that, the more you can discern whether something is amiss, right? So maybe someday in the future we'll see systems that do not provide the ability to challenge it as a potential warning flag that people are operating with bad intentions. Right now, at least the thing that worries me more, as I talked about last time, is these unintentional errors where we unintentionally trigger the idea that a system should be trusted more than it should be. Those I think are really easy to fall into those traps right now. But to come back to where you started, it can be both, right? Maybe a really well-designed system is the one that both helps us understand how to use it better, but also reveals kind of, assurances about its correct working as well. Because, maybe lots of the times when it's not working well is because we've posed ill-formed problems to the system, and understanding why our inputs are affecting the system a particular way is a form of learning how to use the system better, right? So there's a piece of work, I don't want to monopolize here, but there's a piece of work I didn't talk about yesterday where we look at explainable systems, not in terms of the algorithm generating explanations, but users crowdsourcing explanations of the system itself and the sharing their explanations as a form of basically a community helping to understand how to use the system better, right? So someone says, I asked this question of the system, I got this answer, but I rejected that answer because I don't think it was thinking about X, right? So the next person comes along and asks the same question, they also get the answer, but they also get the trace of what everyone else has done. So they can look and say, oh yeah, someone else in this very similar situation asked a very similar situation, and they chose to act on their information for this particular reason. I didn't think about that. Now I'm a little bit more aware of what the system can and cannot do for me. And so, in the end, this is all about, if it's all about actionability, I think we should allow encompassing broader concepts of what explanation, explainability, explaining ability, whatever we want to call it, should mean. And I do like I do like calling it explaining ability.
I'd like to piggyback off of that point on explaining ability. It certainly is nice wordplay there. Is sometimes a very complex model may by virtue of it being complex, not be very transparent, which I believe, Mark, is something you were alluding to. While I think transparent ability may be separate dimensions, there may also be trade-offs there that in certain models. For in the bank loan case, one thing that might be an issue is if you're using a complex model, a lot of times explanations are given with, say, linear local approximations. Based on your decision point, you make a little change and the likelihood of your loan being approved would increase. That may be the best you can do in terms of transparency, and it may seem actionable, but it's also deceptive in a sense. It's very local. It may be that after you make the change, you can't do any more in that direction. Like improving your credit score beyond 5 points doesn't tell you, doesn't really improve your likelihood of getting the loan approved by much. So there's a sense of the limits of the human model as well as the explanation that needs to be considered for transparency. My explanation may seem transparent for me, but if I don't consider how the human is going to extrapolate or interpret that information, I may actually be deceiving them. And that's a dance that I don't know, I think about, but I have no idea how one could address it, because it's very hard to model the end user and how they would interpret information.
Well, that's kind of why I always advocate that we need to study people before we design explanation systems, or design them with the participation of the stakeholders, whether they're end users, salespeople, corporate. There's a whole lot of stakeholders that come into play in these systems. I think there's kind of modeling is two things, right? One is I have expectations of my users. I'm going to design for those expectations, and I'm going to assume that everyone kind of has the same expectations, or I can bucket people. And then there's, something that some people had alluded to yesterday, which is, try to build models of our users on the fly, right? And then use that somehow. And I think these are both ways that we can proceed. I don't really have a deep thought here, just a reaction. I agree it's an issue, and it's something that deserves a lot of study. I think you could actually just kind of study that a lot, and you can even study that without building systems.
Obviously, I'm supporting the idea to study people. And one thing that I think sometimes can be useful is to have an observer perspective. So if a user has a interaction with the system, dialogue or not, an observer can sometimes detect more easily where the misunderstanding happened, what the different assumptions were, where the goal and the attempt to reach the goal were dissociated. And that information by the observer, sort of the diagnosis of what went wrong, can then be used to improve the system, or maybe even give advice to the user to say, oh, it thinks this, so you should ask it that way. So you can then get everything, right? You can get the actionability, you can get better insight in the system, you get improvement of the system, because it next time needs to diagnose or maybe ask a follow-up question to distinguish two possible expectations the user had. We are not as good when we are the ones who are interacting with the system. We are sort of more caught in our own perspective. Recognizing that we make assumptions is extremely difficult. But if somebody observes me, they can more easily see what assumptions I make and whether they match the system or not. So in terms of user studies, I think this could be an interesting approach to take advantage of the distance and sort of the better overview that observers have.
It also sounds like you're advocating for an AI.
Before you continue, I believe Professor Toni will have to leave us. Yes,
yes,
so
I apologize, but I have a follow-up commitment. These are all extremely interesting topics. I think I've learned a lot more from this panel than I imagined before. Thanks for all the other panelists and the participants' questions.
Thank you for being here, Professor Toni.
Bye-bye. Bye.
Bye. All right, we are a bit over time, but we can take about 5 more minutes if everyone is interested.
No, there's no earth-shattering point, so we can end.
Yeah, let's take 5 more minutes. All right, yeah.
Sure, I'll jump in. I think, Dr. Malle, you were alluding towards if there was an observer, is that almost advocating for a separate AI companion model that knows you well and is a mediator between you and a more complex system? That could be, let's quit and start a company. We'll make some money there.
Yeah, that's hard. I would start with humans and take advantage of human observers and their pretty good ability to diagnose problems, not their own necessarily, but other people's problems. And then maybe at some point there could be a system level that monitors the dialogue and has very particular parameters it looks for. It's not necessarily doing the search for the concrete information. It monitors how that dialogue is going and where there might be something missing. So you can have a different level of hierarchy. It's sort of we sometimes try to do this, right? We are the internal monitors of our marital interactions. We sometimes just can't stay there, but if we can, we sometimes notice, okay, I'm just getting too upset here. And maybe systems can do this. They, in a sense, begin to have that observer level. But I would really start with humans because they have incredible insights that are very difficult also for designers to anticipate until you see, oh, wow, yeah, that seems pretty clear what the problem was. How did they notice that? Oh, because they saw this hesitation. And then suddenly the person talked about something else. That is a very important spot. We may have to intervene on that. So those insights, I think, can be made useful. I like the idea of eventually building it in. But I think we can learn a lot from humans first and then start building the meta level.
Just to add to that, I think so learning from observations, especially in the context of explanations, is harder than learning from observations in terms of learning how to act, because we are trying to learn what the expectations of the person was, not what actually happened. And what you observe is actually what happened, not what they thought would happen. So learning from observations is kind of, I think that's where dialogue may help, because you want to actually elicit what was in their mind than what actually observed. So learning from observation is a very tricky part for mental model learning, especially because you never see what was in their mind.
It's like, it's not just dialogue though, right? It's like, it's a library. It's a, you know, it's the whole space of channels. It's hard.
Yeah, I think we haven't been talking about dialogue for a while. I mean, we're just talking about explainability.
Yeah.
So, but this is all, you know, good stuff.
All right, I think we're out of time, but it was that was very, very interesting. I think next time we have to hold like a 3-hour panel to discuss all things. So thank you to all our panelists for being here. That was very fruitful, very, very interesting. Thank you again.
Thank you.
Thanks for the cool questions.
Yes, thanks for all the great questions. Looking forward to more of the workshop.
Yeah. All right, so now we can take a 5-minute break, unfortunately, instead of 15, and then we'll continue with a paper session. We have 3 papers, and right after that, we have Professor Malle's invited talk. All right, so let's take a 5 for now.
The invited talk after this. So yeah, so we'll be presenting. There'll be 3 papers in this session. So starting with Sriram and his work on accounting for effects of human uncertainty. You can get started.
All right. Thank you, Shad. Hello, all. My name is Sriram Gopalakrishnan, and I'm going to be presenting some work on how we can account for the effects of human uncertainty when computing policies for humans to execute. And this will be in the context of problems that can be modeled as Markov decision processes. This is joint work with Mudit Verma and Dr. Subbarao Kamambati. So why bother with computing policies for humans when AIs are going to do everything? Well, there are going to be cases when the AI cannot perform a task. And one instance of this is, say, an out-of-the-loop operation, which is a term used to mean that when the AI fails and you need a human fail-safe operator, we need to give a policy for that human operator to take the system into a stable state or allow it to continue acting. So that's one case where we need human policies. There may also be legal mandates on human actors, such as in medical settings. And lastly, there will be limitations or availability constraints for automation tools. And for such cases, you'll need the human to fill the gaps. So we do have to consider how we can compute policies for humans. Now, when we're dealing with human policy execution, at least in the case of MDPs, we're going to focus on when the human is just executing a policy, not coming up with your own policy on the fly. So when executing a policy, the process would be the human identifies a state and executes the associated action. Now, when doing so, there are some problems that might arise. They may not exactly know what state it is. They may have some uncertainty as to that state. And to resolve that uncertainty, they may take additional perceptual actions outside of the normal ones to resolve it. And then they take the policy action associated to their best guess. This may be incorrect And these are the two problems that we're trying to tackle: this behavior under uncertainty and errors. And if we can account for it, we can improve the outcomes when the human's executing a policy. Now, in this problem setting, we assume that the human has perfectly memorized the problem, or they have access to a chart, so memory issues are not considered in our problem setting. So to help build some intuition, let's consider the case of a warehouse worker who is packaging products into boxes of different shapes. The states in this setting are the size of the order, which could be a small, medium, or large. This also corresponds to the actions, which say package in a small box, medium box, or a large box, and if bubble wrap is needed. If the human worker tries to package a large order in a medium box, then there'll be some residual items that will require an additional box. The extra sensing action in this setting corresponds to, if the human's uncertain, if an order is medium or large, they may take the largest item, place it next to a box and see, would this fit in? And then decide which box to use. These extra sensing actions have a cost, in this case, a time cost associated with doing them. So ignoring them would actually be detrimental for the policy. An example here of a policy that considers the type of errors humans make would be to tell the human, always use the large box. The boxes are all cheap, so we don't care if you have to use the perfect size box. This means that they'll spend less time trying to determine the state correctly, less uncertainty, more throughput, and more rewards. So that's a benefit where if we consider the human model in the setting, we can get better outcomes. So the problem motivation here is modeling human uncertainty that can result in errors and delays, and also how the human responds to that uncertainty, extra actions. Now, if we can account for these errors and behavior under uncertainty, we also minimize the need for explanations, because if we penalize or correct the humans, then we're going to have to spend extra time explaining them, which can be expensive in certain settings. The approach we take is to build a problem-specific model for state inference and their response to uncertainty, and compute a reactive controller based on it. I say reactive controller because uncertainty makes the MDP a POMDP, unfortunately. And the way we compute this controller is using a policy iteration method, which is heuristic because it's a POMDP, as well as a branch and bound method, which will give you the optimal policy, but unfortunately, it's only suitable for smaller state spaces. The problem formulation uses the usual components of state, action, transition, reward, and discount factor, but we also consider as input the likelihood of a state being the initial state. And perhaps the two most important parts to our approach is the human model and the set of parallel states, which are states reached when the human takes an extra sensing action. These states have the same dynamics as the underlying MDP state, albeit they are only reached when the human takes an extra sensing action. It captures the updated human inference likelihoods and folds it into the state space. Hopefully, some of that will become a little more clear when we talk about the human model. Now, ideally, we'd like to evaluate full policies on the human, but the space of policies are very large. And since we're only trying to compute a reactive controller, we can focus on the proxy task of state identification, because the only part that the human has to do in this setting is figure out what state it's in and then follow the policy as given. So for this proxy task, we build the human model as follows. For the human's inference likelihood, there are two terms, PC and PU. PC, or think of it as a probability of classification, tells us how likely the human is to infer a particular state given the true state is, say, S2. So in our warehouse worker example, if it was a large size order, how likely are they to confuse it with a medium sized order and take the wrong action? PU, on the other hand, is the likelihood of the human inferring a possible set of states. So this means if the true state was S2, how likely are they to infer that the possible states are S1 or S2? in our warehouse worker setting, if it was a medium-sized order, how likely are they to think it's only medium or small-sized order? So those two capture the inference likelihoods. But we also need to consider their response to uncertainty. And that's what the two terms psi0 and psi1 tell us. The psi0 term gives us the baseline likelihood of taking an extra sensing action. Maybe they had to count the number of products in the warehouse worker setting, and they may miscount it 5% of the time. So regardless of what they infer, they want to take an extra sensing action. So this is the baseline likelihood of that extra action being taken. Additionally, if they infer two possible states, two or more, and the policy conflicts between these states, then they'd have to try and resolve that uncertainty. The likelihood of them taking extra sensing actions to resolve that uncertainty is given by psi1. Now, all of these terms come together in this equation. I promise it's actually quite straightforward, and we'll step through it. This equation tells us the likelihood of an extra sensing action, which is represented by A plus, given a particular deterministic policy. This likelihood is given by the bias likelihood, psi0, and is higher when the human infers a possible set of states and the policy is different across those possible set of states. This is what the second line in this equation tells us. Now, of course, the human is not only taking extra sensing actions, they also have to take policy actions to do the task. And the likelihood of a policy action is determined by the likelihood of the human inferring a state given a particular ground truth state, which in the second line is given as if the human infers state S1 and the policy action for S1 is A, then that likelihood is increased for that state. The approach we take to tackle this problem is a policy iteration approach where we look at all possible policy changes to every state and change one state policy at a time. There's no optimality guarantees, since this is a POMDP, and policy iteration will not guarantee to give you the optimal policy. So we'll have to do a bunch of random restarts to get better policies. The branch and bound method that we present in the paper does give us the optimal policy and uses a novel upper bound to prune the search space. However, it's only suitable for smaller state spaces, and the search tree does blow up very quickly for larger state spaces. For our computational experiments, we looked at grid world and the warehouse worker setting that I described earlier. In the grid world setting, the likelihood of state confusion is given by the L1 distance, and the lion's share of the reward is obtained when the agent reaches a goal state. There are also small differences in action costs, as well as an extra cost if the human takes extra sensing. Extra sensing here would correspond to the human looking around trying to figure out where they are. In addition to the computational experiments, we also did some human subject experiments to see if our intuitions translated or can be substantiated in any way with human subject experiments. So in this, there's an underlying MDP grid where the states are represented by colors. And we intentionally chose two similar shades of red and two similar shades of green to try and induce some uncertainty. And what we would do is flash a particular color for half a second and ask the human to press the arrow key corresponding to that color to move through the underlying MDP grid. Now, the human was presented with two policies. This was a within subject study. One of the policies was the optimal MDP policy that did not account for uncertainty or the errors that the human might make. This is the first policy on the image on the right. We also presented the same human with a policy that did account for uncertainty, where the two red states had the same action. And in this case, we saw that the human following the policy that accounted for uncertainty gave higher reward accrued with a statistically significant difference. Now, the way we built the human model for this problem was in a separate phase where we flash a color and ask them to tell us which of the colors from the list on the right that they think it was. And if they were uncertain, they could choose to see the color again, which corresponds to the extra sensing action in this human subject study. So to put all the pieces together, for the problem of computing a policy for humans to execute, we first built a model of human inference focusing on the proxy task of state identification. And we modeled their response to uncertainty during execution by considering that they will take extra sensing actions to try and resolve uncertainty. We then use this model to compute a reactive controller, and we present two approaches to compute it, a heuristic approach, as well as a branch and bound approach that gives you the optimal policy. An extension to this would be to try and compute history-based controllers, where we would ask the human to track the history of states and then execute a policy based on that. This would give better outcomes in a lot of settings, but it's also much more expensive to build a human model for this particular setting. Thank you, and I'll be happy to take any questions.
Thank you so much. So we do have time for 2 or 3 questions. So if anybody has a question, feel free to raise their hand or unmute yourself. So while we wait for that, I had a few questions. So one of the underlying assumptions here is that the human would accept policies that are like specified by an AI agent. Have you given any thought on like how likely are those? Like in certain scenarios, right? Like is this always going to work? The other thing is, have you given thought about how you can design policies that are robust to the kind of changes the human might make, right? After a while, people might try to come up with shortcuts on how to do this, right? And that might not work out all the time. Have you given some thought on that?
Yes, this was actually a point made by Dr. Matthias, who's unfortunately not here, but he also pointed this out, that once the human starts acting in the space, they may build familiarity. And this familiarity, they might now think, oh, I think I know how to do this better. And they'll start introducing their own policy changes. That's not something I account for here, but that's very much a longitudinal interaction that is likely to happen. You'd almost have to be dictatorial in saying, just follow this policy, don't get very clever, in order to maintain the performance. But I'd say this is the starter policy, and there's still work to be done in terms of longitudinal interactions. And when they start getting better is when they also will start asking questions like, why this action? Why can't I take this alternative action? And at that point is when explanation melds into this problem.
But you see some form of like a monitoring system. I know it is getting dystopian right now, but at least there's some monitoring system making sure people are doing what they're supposed to do. But at least that's one possible approach, like you would imagine.
Absolutely. I mean, in the warehouse worker case, like in companies we shall not mention, they are basically rewarded based on how many products they get packaged and shipped. So that's a real world case where such a policy could apply.
I think we are unfortunately out of time. Sorry for
no. Thank you for the questions.
Yeah. So I think we'll go to the second paper. I think it's Yale. If you are the authors from the second paper here, feel free to share the screen. Yeah. So feel free to start whenever you're ready.
Sorry, I was on mute. Okay, so hi, my name is Yael Septon, and I'm going to present Dr. Ofra Amir and my work, Integration Policy Summaries with Reward Decomposition Explanations. Our work focused on explainable reinforcement learning, or in a shortcut, Explainable RL. So Explainable RL focus on explaining RL agents, meaning agents that have a sequential decision-making process on a large state space. So these agents need to take a decision based on their reward function and the environment, while its decision might change the environment. So they do not make only one decision, like a classifier. They need to make multiple decisions, which means that the current decision an agent makes is also influenced by the future. So for example, we can see an RL agent of Pacman, and we can see that his decision that it makes influence the environment by eating points, and then they disappear from the environment. So there explanation, and we will focus on global and local explanations. So a global explanation explains the general behavior in a high level. And an example for this kind of explanation is a video summary, and we will expand on this more later. And the second type of explanation is a local explanation. So a local explanation explains a specific action in a specific state. So for example, is reward decomposition and saliency map, and also we will see more on this later. So the motivation for combining these two methods is to give a better and more deeper understanding for the user's behavior, for the agent's behavior. So these two methods complement each other, because while a global explanation gives a broad explanation of the agent's behavior, the local explanation explains a specific action. So in previous work, Huber et al. Combined local and global explanations. Saliency map a local explanation and highlights a global explanation. So the highlights is a global explanation that gives a video summary of the agent's behavior. And we will expand on this more soon. And saliency maps give a local explanation as they focus on an image and highlight what was the main features for the decision. So in the example we can see here from the paper, we can see that
I think the speaker, I don't know if it's just my issue. The speaker seems to have gotten stuck.
No, it's the speaker, because we also are in Teams.
She's still in the call. The video's gone now.
Yael, if you can hear me, could you try to restart? Okay,
Maybe message her.
I'll message her.
Okay.
Okay, she's out of the meeting now. We can either wait a couple of minutes, or
yeah,
we can.
I think we can wait a few minutes, because I don't think we are at, like, in terms of time, I think these things we could share.
Yeah, I don't know how to get a hold of them.
Let's wait till 10:10, and if she's not back, maybe we can move on to the next paper.
Unexpected issue with online meetings, online workshops, conferences. What is the time looking?
Well, at least in my end, it's 10:08. So.
I've been someone's messaging me to asking me to tell a joke, but unfortunately I don't know any. So.
I'll tell a joke.
Oh, good. Go ahead.
Please.
Google's Lambda is sentient.
Good one.
I am so sorry. My electricity fell, and with that, everything.
That's okay. No worries. We waited for you.
Oh, sorry. Okay, I'll just continue from where I stopped.
Yeah, please do.
So I was explaining about saliency maps. So in this stage, we can see that what in the saliency map, what is highlighted in the Pac-Man and the points nearby, which help the decision. The results of this study showed that the combination didn't have better results than just having highlights by its own, meaning that the local explanation didn't improve the user's understanding. In our work, we combine highlights with reward decomposition. So while highlights give a broad look at what the agent's behavior that by previous work was established to be a good global method, reward decomposition focuses on explaining a specific state. So both methods don't require previous knowledge, as understanding the results is simple. And in addition, this combination supports both users that are more visual, the video summarize, as well as users that are more driven by number, the reward decomposition graph. And our objective was to see whether the combination of these two explanation types, global highlights and local reward decomposition, help users to understand the agent's behavior. And to do that, we created a user study on a highway domain. So in this domain, the agent is the green car and all blue cars are part of the environment. And the agent can move between lanes, right, left, and change his speed, go faster or slower, and take no action. So when two cars crash, they turn red. So here's a small example. Our agent is driving on the highway and two cars crashed, so they turned red. So we chose this domain since we assume that for all adults, no prior knowledge is needed, as well as it is easy to rely to and understand the significance of the study, which hopefully will lead to participants to be more engaged, which will lead to more reliable results. So in our domain, the agent has 3 different reward types: being in the rightmost lane, speeding up, or changing lanes. So as we said before, our global explanation is highlights. So highlight is used on MDP models and more specifically on RL agents. And the main idea is to give a video summary that describes the agent's behavior. So the idea is taken from the real world. Let's say a heads counter wants to recruit a basketball player. So instead of coming to a game and watching the whole game, he can just see a highlight video that shows the player what the player did in different scenarios. So the same thing can be applied on RL agents, where the different scenarios are that are chosen by how important they are. And we will soon explain of how we determine this important state. But before that, a little reminder. So for every action in every state, we calculate the Q value, which represents the reward the agent will receive from the immediate action, plus the estimated future reward. So the action that is chosen is the action that has the highest Q value. And we determine the importance of each state by the difference between the highest Q value and the lowest Q value. And the higher the difference between the Q values are, the more important the state is. And the reason for that is because we assume that the chosen action had a big impact on the results. So here's an example for a highlight summary of the on the highway domain. So we can see our agent going to the right most lane when it's possible. And now it's not possible, so he's just going in between lanes. So the second type of explanation is a local explanation, and we focus on reward decomposition. So the idea of reward decomposition is to decompose the Q values. So instead of getting a Q value for each action, we will see for each value in the Q value what it is created from, meaning how much each reward type contributed to the Q value. So for example, in our highway domain, we can see that in this specific state on our right, the x-axis is the action and the y-axis is the Q value. So we can see that the action that is chosen is the right lane, as it has the highest Q value. And we see that the right lane reward type contributed the most to this action, and changing and speeding up contribute the least. And we could see that if the agent will go to the rightmost lane, he will most likely won't be able to speed up as he has a car in front of it. And we created 4 different agents with different preference, 3 agents that are similar in the sense that they all have combined of 3 different reward types, and another agent that has only 1 reward type and therefore should be the easiest to detect. So we conducted a between subject study with 164 participants, and each participant was randomly selected to 1 group out of the 4. So the first one is frequency sampling. So this is equivalent to say random, but we take into account that states that appear more have a higher probability to be chosen. The other one type is highlights. The third is reward decomposition, and the fourth is the combination of both explanation. And in each group, participants saw all 4 agents. So for frequency sampling and highlights, the participants saw 8 different scenarios that were displayed by 8 video summaries. When in the highlight condition, each scenario button jumped the video to the important state, and in the frequency sampling condition to a random state. So this is a screenshot from the survey. So when they pressed scenario 1, the video jumped to second one, which was the important state that was chosen. And in the condition frequency sampling and reward decomposition, frequency sampling with reward decomposition and highlight with reward decomposition, the participants saw 8 different scenarios that were displayed by an image, and then that describe the state, and then a reward decomposition graph of that state. And when the highlight and reward decomposition, the state that was chosen was the important state, and in frequency sampling and reward decomposition, the state that was chosen was just a random state. So for each agent, they were asked to rate what reward type do they think the agent preferred. So an example, do they think that the agent preferred speeding up or changing lane, or had no preference? So this was asked for every 2 reward types. And their answer was based on the type of explanation, as you can see on the image on the side. So our results show that in total, there was no improvement when looking at the combination of highlights and reward decomposition, and that highlights alone did not improve more than frequency sampling. And that just reward decomposition was significantly better than highlights and frequency sampling. And these results don't align with the previous work that was presented. Their highlights by itself, the global explanation had the most significant impact. And in our work, the reward decomposition, the local explanation had a more significant impact. And we assume that the reason for that is that we use too many examples. So a small reminder, for each agent, the participants were given 8 scenarios. And we believe that this lowered the effect of highlights, since when giving too many examples, highlights becomes less relevant, since also without it, the participants saw enough examples to have a good understanding of the agents, specifically in this narrow domain. In addition, the task was oriented towards reward decomposition. So the question that were asked were exactly what reward decomposition showed. So we assume that this had a better impact for reward decomposition. For future work, we want to expand and do this on more domains to see that the results aren't specifically to the highway domain, sorry, and also use different combination of explanations. Any questions?
Thank you so much. So interesting talk. Unfortunately, we don't have time for too many questions. If anyone has a quick question, they can ask now. But you can, yeah, go ahead. I just want to add, everyone can follow up with the authors in the Slack channel. So there is option for more discussion later. But please go ahead.
Yeah, I have a quick question. So I'm not familiar with the global explanation approach for the Q values, but it seems that you're kind of biasing towards actions that will be performed by the reinforcement learning agent, i.e. the Q values being higher, the difference between those. But I mean, could it be the case that actually important parts of the solution are what the agent chooses not to do as well?
That is an interesting approach. But at the end, we see what the agent did choose. And even in the highway domain, you can think about the real world. If you miss a turn on a highway and you don't turn right and you did a mistake, it has a big impact rather than doing this mistake on a local road. So even by not doing an action, eventually you choose the action that gives you the highest Q value. So also if you did a mistake, then the difference between the action that was chosen and that was not chosen would be high.
Okay, yeah, thank you.
Thank you so much. Maybe the next authors can start sharing the screen.
Can you see my screen?
Yes.
Okay. Just a sec. Okay, so hello everyone. I am Pulkit Verma from Arizona State University, and I'm going to talk about JEDI, a system for skill-aligned explainable robot planning. And this is a joint work with Aman Shah, Trevor Engel, and Siddharth Srivastava. And these are the people who have made contributions to this project at various points of the development. Yeah. And now moving on to the actual talk. So JEDI is designed for outreach and educational efforts aimed at helping even non-AI experts to work with AI systems that can use symbolic planning. Now JEDI features a simple drag and drop interface using which the users can create a plan to achieve a goal in one of the 5 robotic domains that we provide. And if the plan is successful, they can see the plan's execution on simulated robots. I will show a demonstration at the end of the presentation. But before that, let's see what specific problems we solve here. So JEDI overcomes 3 technically significant challenges in making AI planning more accessible. The first challenge is the fact that inexperienced users will have no knowledge of the low-level constraints that real robots need to conform to. So we must somehow bridge this gap in expertise of these users because we cannot reason them to, we cannot expect them to reason like what each joint values of the robot will be. The second challenge follows from the first, and even if we can show users simple abstract representations of the robot's capabilities, that isn't much of a help unless we can efficiently convert back from high-level plans made of abstract actions to low-level motion plans that are suitable for a robot to execute. And finally, the third important challenge that we address here is helping users to understand a planning problem in a better way by computing personalized user-specific explanations automatically. Now let's see these subsystems that allow JEDI to overcome these challenges. So JEDI is built from a few key subcomponents that work together with the Blockly visual programming interface. Here you can see JEDI's architecture. We'll now briefly go over each of these components in detail. So the first component is a task and motion planning system that handles the autonomous refinement of high-level plans provided by users down to low-level motion plans that the robot can execute. So this system takes each of the action in the high-level plan and tries to concretize it into a low-level motion plan. And for this, we use a system called ATM MDP that was developed by Shah et al. The next subcomponent is an algorithm for computing personalized explanations for plans that fail. So JEDI asks users to put together action plans with visual blocks to solve the problems, but it can be hard for novice users to meet every necessary condition to create a correct plan on the first try. So when users submit a plan that will fail, like so, then JEDI displays an explanation that tells them what exactly went wrong with their plan. And for this, we use Helm that was developed by Sridharan et al. Now, finally, one of the barriers currently standing in the way of non-AI users who want to understand and interact with planning agents is the formality of the symbolism used by these agents. So JEDI deals with this issue by using a third component that ties actions and predicates in a domain to snippets of natural language that can be combined into coherent sentences. And this allows states and actions to be expressed in a way that is less intimidating to users who don't have much exposure to concepts like predicate logic. Now let's see how JEDI brings all these things together using a demonstration. Okay, yeah. So JEDI users first need to pick a domain and a problem to work with. And here we give a set of 5 domains. And for each domain, we have an associated problem. And then we show the goal to the user that they have to achieve. It is also defined in English and showed as an image. And then there are some actions that the users can choose over here. And they just have to drag and drop to create a plan. For this demo, what I'm going to do is use a plan that we already created because it takes time to create and refine it. Yeah. So now what happens if the plan fails? So in that case, here they can see, sorry about that. Yeah, so if a plan fails, it gives an error that, okay, the action at step 1 could not be performed because a particular plan was not held in the correct hand. So these kind of error messages come, which are actually explanations of why this particular plan that the user submitted has failed. Yeah. Now, if we try to execute a plan that is correct, so for this, I'll again use a plan that we already created. So for a correct plan, this system tries to generate a motion plan first. And once the motion plan is correct, the users can see the simulated robot execute that particular plan in this simulator. Here, the Yumi robot is making a 3-story pie structure as given in the goal that we saw earlier. And this video is sped up 3 times because this actually takes time to execute the actual plan. And to help users getting started with this system, we provide a documentation and a video tutorial. And the code is also provided, and we also provide an already configured virtual machine for the users to use. Currently, the system comes with 5 predefined domains and a fixed set of problems to solve for each of those domains. And we plan to extend this set to more problems and domains. We also plan to improve the quality of the motion plans. As for now, like we currently use the standard motion planners that are available, and they might generate plans that are not intuitive to the user, right? So, for example, the hand is starting from a location A, and then it will make a weird rotation in the space to go to a point B, whereas it could have directly moved from A to B. So those kind of issues we have to fix. And finally, we plan to conduct a user study to evaluate this system at some point in the future. So with that, I would like to thank all of you for listening, and please visit our website to learn more about JEDI. If you have any questions, you can ask now or contact me in the Slack channel. Thanks.
Thank you so much. Again, we don't have too much time for questions, but if anybody has any quick questions, yeah, I think Ben. Again, people can contact Pulkit on Slack.
Yeah, I have another quick question. Thank you very much for the talk, and great name, by the way. So, sorry, maybe I missed it in the talk. These things like is lying horizontally or is in left hand, you know, those parts, is in, is lying, etc. How are those generated? They already put in a priori, or is there something that you use to
Yeah,
get
so
semantic knowledge from the plans?
Yeah, so the domain is already there in the backend, right? And that is defined in terms of some predicates. We just show the interface in terms of natural language. So each of the block has these English representations of those predicates. So like
okay, so the English representations of the predicates are inputted.
Yeah.
Okay. All right. Great. Thank you.
Okay, great. I think it's time to move on to the invited talk. I'll hand over to Sylvia.
So yes, so hello everyone once again. I think you had already the chance to talk about explainability with Bertram, but I will introduce Bertram Malle, which is the next invited speaker. If Bertram is here.
He's not here yet.
So I won't introduce him now. I will wait for him just a bit. We will wait for him just a bit. Maybe we can drop him a message. Was it supposed to start now? Yeah.
Yes, so I think our timing was certain.
Let's wait a few minutes. Yeah. Hello. Hey.
Hi, sorry for the delay. I'm going back and forth between meetings and email crises. And I wish I had had more time to actually engage with the rest of the workshop. This is the one disadvantage of doing it remotely. You don't have the excuse, oh, I'm gone. Sorry, I can't have any meetings. I'll be away in Napoli or Berlin or wherever. So unfortunately, life.
But you are perfectly on time. It was perfectly on time, just that we were already panicking. So yes, I was going to introduce you because even though you spoke during the panel, we didn't provide an introduction of you. So the next invited speaker is Bertram Malle. Bertram Malle earned his master's degree in philosophy and linguistics and psychology at the University of Graz in Austria. And after he went to the US and received a PhD at Stanford University, then he joined the University of Oregon Psychology Department, and since 2008, he is a professor at the Department of Cognitive Linguistics and Psychological Sciences at Brown University. So he received the Society of Experimental Social Psychology Outstanding Dissertation Award. I wish you could give me feedback on how I should write a thesis properly. And yes, he is the past president of Society of Philosophy and Psychology, and Malle Research has been founded by NSF, Army, Templeton Foundation, Office of Naval Research, and DARPA. He has distributed his work in many articles and books and on the topics of social cognition and specifically on intentionality, mental state inferences, behavioral explanation, and moral psychology. And now he is also working a lot in the context of human-robot interaction and moral competences in robot and social assistive robotics. So his work is quite relevant for what concerns explainability, especially the part that relate with behavioral explanation and how we attribute intentionality to agents. So I will leave him the floor now. If you want to share your screen, please go ahead. And thanks a lot for being here today.
Thank you, Sylvia, and thank you for having me. I am happy to have a chance to tell you a little bit about empirical research, which is, as a psychologist and cognitive scientist, it's the one thing that I'm trying to contribute that isn't always part of the discussion in AI and robotics, and I think has some increasing significance. Let me just double check. Do you see the Zoom pictures, or do you see only my screen with the slides?
I see only the screen with the slide.
Perfect. And there's nothing in the way.
No.
Wonderful. So this is work in collaboration with Danny Ullman, who's now working for for Facebook, and Beth Phillips, who was a postdoc and is now a professor at George Mason University. And there have been many other people, including Matthias Scheutz and others, who have contributed to bits and pieces of this work. Let me start with just my interpretation of what XAI is charged with, probably among other things, but it is charged to address concerns of transparency, trust, and ethics. These are typically the terms that are used that are supposed to be helped, issues that are helped with, facilitated, maybe resolved, or at least improved by way of making systems explainable. And the question is whether explainable AI can really do this. So the first step is to think about the functions of explanations. And this is a little bit what our panel discussion really touched on, is first of all, as a cognitive function, that's simply to create meaning. I might read a book, I might observe events out there through my window, and I might just be confused and try to make sense of it. And the explanation is entirely in my own head. So I understand what a particular event stands for or what it stems from. I'm worrying about whether I really understood the meaning of a word. These are all forms of cognitive explanations. They are answers to why questions. They also can be variants like what for, where from, or how. But fundamentally, they are why questions or questions that have a cognitive gap in some sense that can get filled. But the social function of explanations is really to manage interactions, to manage those cognitive gaps, knowledge gaps, to remove an audience's confusion. For example, why in the world I would show a picture of tulips with blue flowers in the background, merely as a demonstration. That is an explanation that now makes sense, and that's all that needed to happen for you to understand why I did this. We might also reduce our collaborators' uncertainty about what we are doing, why we are doing it. They may then also have a better idea of how to coordinate their actions with us. We might mitigate somebody else's disapproval by explaining why we did something that may at first glance seem to have been immoral or at least questionable. By giving an explanation, we might change that moral thinking that the other person has about us. So it's clear that in many ways, transparency can be improved, if not always completely achieved, by offering explanations. But really, it's not so clear whether trust and concerns of ethics, ethical competence, moral competence can be achieved. And that's what I'm going to spend the rest of this talk on, mainly to explore these two topics, trust and then the idea of moral competence. So let's talk about trust. And really what I'm talking about here is how people conceptualize trust. Now, I'm going to start with what researchers, scholars typically do to conceptualize trust. Burke and colleagues in 2007 had a paper in which they collected 24 or so definitions of trust from the literature. That was mostly the human-human interaction literature, business literature, social psychological literature. And then we took those explanations and classified them into sort of broad elements because we wanted to build a definition of trust that integrates many different perspectives. And these were some of the elements that we found. Almost all of them mentioned something about the dyadic nature of trust, that there's a trustor, an individual, a person, a party. There's a trustee, the other one whom you trust in could be a collective, could be a government agency, could be an individual person. And there's some kind of relationship between them. And the words interdependence, interpersonal interaction come in here. A second key element is that when you trust, you accept some form of vulnerability. There's a risk and you decide to trust, or you have a sense of being able to trust despite the possibility that the other might exploit you, might make fun of you, has some power over you, or simply through a mistake could hurt you. And you have to accept or be willing to accept this vulnerability. That's part of the nature of trust. Merely doing something that you don't know could cause vulnerability doesn't necessarily mean trusting the other. It's just going along with, and that's a different concept. It's almost always about a future action. It hasn't yet happened. I trust that you will do something, that you will behave a certain way, that you will not do something, that you will fulfill your duties, and that at least I can trust your intention to do it. Not always will your intentions be fulfilled because the world sometimes is in the way. All of that is in the form of expectations or beliefs. I believe that I can be hurt, that you have the power, but that you will do differently, that our relationship will protect me. These are assumptions, perceptions, beliefs, and it's a subjective state, therefore. Now, what it is that I'm expecting or believing falls into several domains, and this is key for our contribution to rethinking human-robot interaction, aspects of trust, human-robot directed trust, and human-AI directed trust. The domains that people have mentioned is that I may have an expectation that you are benevolent, helpful, that you have concern for me. I may have a different trust that you will be honest, fair, that you will show integrity, or that you are reliable and predictable, or that you have ability, competence. And even though those numbers of occurrences in these definitions weren't as high, we then, as you will see in a few slides, showed that these topics keep coming up consistently in the literature on trust. So we kept that in mind and then constructed a first study in which we just gave people a list of the kinds of terms that could be objects of trust or issues of trustworthiness. And we at first thought that there's a two-dimensional space, something on the side of capacity trust that also automated systems can have, and we can have towards them, and something on the score of personal trust, interpersonal trust, social trust. And we thought that that might be a good dimension to start our work with. So we gave people 62 of these trust-related words and asked them to basically rate them along this bipolar scale. And then turn out when we analyzed the covariance structure among the ratings, so some of these trust-related words were highly positively correlated with each other, others were negatively correlated, some were not at all correlated. Something that is called eigenstructure that many of you probably know from a different context can be extracted. It tells you what a possible correlational pattern is in there. And what we found was strikingly that even though we gave people only a bipolar scale, what seemed to happen is that they grouped the terms into 4 larger dimensions that were largely uncorrelated. And these dimensions, as you see, can be roughly described as capability, something about ethical capacity, sincerity, and reliability. And that was striking, that a two-dimensional space by a single scale applied to 62 trust-related words has a statistical structure, covariance structure that is 4-dimensional, was really unusual. So we said, okay, we need to follow up. So we planned a second study in which we asked people to sort a selection of these trust-related words, the ones that were most clearly representative of those 4 dimensions. We also had a few fillers just to make the task have sort of a little control condition there. And we asked them to sort them into 4 bins. Now, in this study, we labeled the bins because we wanted to almost have a sanity check that people really can reliably recognize what we labeled as the key category names: capable, ethical, sincere, reliable. And you will see later, we have a version of that where we don't even give them the labels. But for now, we gave them the labels, and we had a 5th category, other. And we expected that most of the filler terms would come up in the other category. The result was, again, a nice 4-dimensional structure. And you see here, the green shaded ones are those where a very high percentage of participants all agreed that this word reliable, or a phrase you can count on, or you can depend on, you can have faith in, those phrases fall into the category of reliable. Other phrases fall into capable, and so on. And we also found, for the most part, that our filler words were in a separate category. Interestingly, benevolent fell into this category as well. And at the time, we took that to mean that benevolence really falls under ethical and it's not its own dimension. And we had to then revise that assumption, as I'll show you in a second. We then conducted a literature review to see whether those 4 dimensions are not just in people's heads, but actually characterize what people theorized about trust. And what we then found was that really there were these terms, but virtually none of the theories had all 4 and then that possible 5th one, benevolence, in their theoretical framework. Several of them talked about competence and reliability, but also others talked about these more moral dimensions of integrity, sincerity. And then we were struck by the fact that many mentioned benevolence. Now, they might have been wrong. It might be that in people's own conception of trust, benevolence just falls under ethical integrity. But we had to seriously consider that our initial task was just not able to capture this 5th dimension. So this was then the motivation for a 3rd study in which we went back to our sorting task, but made a few changes. First of all, we used, again, 41 trust-related words and gave people a choice to sort them in any number of bins, 2 at least, but any number, 2, 3, 4, 5, 6. And we didn't label the bins. So we asked for a conceptual structure that we did not impose, and we expanded our word set to feature a number of aspects of benevolence, such as, let's see, what do we have? Benevolence shows goodwill, kind, and so on. So these were roughly about 6 to 8 words for each of the possible categories. And we, again, browsed the literature to make sure that we cover all those domains very well. So we also asked people, after they did the sorting task, to label the bins. So once more, in the original study, we labeled them. This time we didn't label them, but we asked people to give a label. All right, what were the results? First of all, 74% of people created 4 or more categories. So it really seemed that this semantic space of trust-related words falls into a multidimensional domain where at least 4, maybe even 5 or 6 dimensions characterize the distinctions that people make here. The dominant labels reflected just the categories that we had hypothesized. So these were the terms that people gave as the most frequent labels for the first 5 bins: competent, dependable, moral, honest, and caring. And these map exactly onto the 5 dimensions that we had hypothesized. This was the number of times people used these labels. The next most frequent ones were skilled, reliable, loyal, authentic, and kind. Those are the frequencies. So once more, the most frequent labels fall nicely into the 5 hypothesized categories. And also true for the next 5. So this is without giving them any guidance. Not only do they pick typically between 4 and 6 categories to sort those semantic phrases, words into, but they also label them just by the terms that theoretically we expected to characterize trust, namely as a 5-dimensional space, once we added benevolence as a valid 5th dimension. Interestingly, they did use trustworthy in sort of a moderate frequency, but trustworthy was not associated with any particular one. It was sort of the more general term that showed up, but was not characterizing one single dimension. It is really the next level of abstraction you can think of, but doesn't tell you enough about the domains of trust. Then we also analyzed the co-occurrence patterns of the specific words to see whether, once more, a statistical structure can be detected. So you basically look how often any one term co-occurs in a given bin with any of the other terms. It didn't matter in which bin, just how often do we sit in the same bin with each other. And then we analyze the data in multiple ways. Here is a cluster analysis, k-means clustering, and we project here the clusters that the system extracted, namely 5, down into a 2-dimensional space. And they nicely fall into 5 large groups that literally capture the words that were hypothesized and had previously in our other tasks been associated with the large categories of transparency or honesty, you can call it openness, genuine, authentic. All of those are part of the same dimension. Ethical integrity has things like ethical, moral, respectable, principled, fair. We had benevolence, very clearly its separate category of keeping others in mind, having goodwill, being kind and caring. And then the more performance aspects of dependable, predictable, consistent for reliability, and expertise, skilled, capable, and so on for competence. And we then created the same version of structures using multidimensional scaling, hierarchical cluster analysis, network analysis. They always replicated as the underlying conceptual structure that people seem to have about the space of trust, the language of trust. In the meantime, we also created measurement scales, 4 items for each of those dimensions. And this is publicly available. You can download that. You can just Google for MDMT, Malle, or Ullman and Malle. You can use that. It's a short 20-item scale. We've now used it with just 10 items, 2 per dimension. And we find quite nice differentiation, virtually always between the moral on the left here and the performance side on the right, but sometimes also within any one of those larger factors between the specific dimensions. So that's a useful tool because it can cover certainly the human-human trust domain, but it can also cover the human-machine trust domain where in the simple automated system, all you care about is reliability and competence. Ethical issues just don't come up. And we allow people to just simply make a check mark does not fit. We don't force them to make ratings if they just don't make sense. But as you interact with social robots, with assistive care robots, some of these moral dimensions really are important. Whether the system is authentic, sincere, has goodwill, has your interests in mind, is principled, knows the moral rules, those are concerns that really will come up and do come up already. And we see this in some of our early studies. So we can now say that we can reconstruct trust as a subjective state that is a set of expectations, perceptions of properties of the other agent that we can call properties of trustworthiness. This is not the only way trust can arise. I can just simply inherit trust through my social community, through habits, what I believe the expert tells me. But in many cases, we do collect evidence of trustworthiness, and trust is in a sense a result of, or a combination of, our expectations of how transparent, ethical, benevolent, reliable, competent a system, a human, a group, an institution is. Though in not all of the cases do we have knowledge or expectation about every one of those dimensions. Now, if trust reflects evidence of trustworthiness, we can go back to our question how explanations help with building trust and maybe recovering trust. And that's now what I want to go through dimension by dimension. How do explanations provide such evidence, or in principle could provide such evidence? If you look at competent and reliable, the performance overarching factor of trust, I will show you some typical evidence and then what explanations could do. And here I'm talking mostly about machine explanations to an audience. So these are the explaining ability aspects. But in principle, you could also think of an expert explaining it to a user. But more interesting really are those M to A explanations. So typical evidence for competence would be reaching high quality standards, mastering a new challenging task. And explanations could declare what quality standards the system aimed at, or show recognition of the task challenge, how difficult the task was relative to its own assessment. Self-assessment is, of course, part of an explanation of this sort. Evidence for reliability might come simply as the same performance over time, having no surprise, no variation, little uncertainty. That would be evidence for reliability. Explanations could reveal something like consistency standards, the idea that you always try to do the same thing, even when the situation varies slightly, you are reliable. Now, reliable can be at a pretty low level of competence. So these two dimensions are really independent of each other. You can also be appearing to be reliable, but because it simply is the case that for some tasks you are competent, for others you are not. Now, the moral superfactor of dimensions transparent, benevolent, and ethical can also be analyzed that way, but the explanations become much more sophisticated. Transparency, the typical evidence might be speaking the truth. being intelligible, not deceiving. And the way you can reflect these properties of trustworthiness in explanations would be to reveal the real reasons for actions, not just the purported reason, but what the actual motivation was. Or in fact, referring to sincerity norms, saying that, you know, you might not want to hear this, but I want to be honest, this is why I did it. So this would be very powerful evidence for transparency. And I'm not saying that this is necessarily what robots and AI can do. This is the overarching analysis of what explanations might be able to do. Evidence for benevolence would be recognizing others' needs, taking risks for others, investing time and effort. And then explanation could, for example, refer to the outcome that one intends to achieve, that it's the other's positive outcome that one tried to achieve, that one was willing to take some risks in order to achieve a certain outcome that is in the interest of the other. So you explain your intention because sometimes you might fail, and still explaining the intention might help to show your benevolence. And ethical integrity is basically the most general way in which this moral competence manifests. It's evidence of following norms, being aware of community values, maintaining principle even when tempted. And that's, of course, especially true for humans, who have always the selfish streak that conflicts with community interests. And explanations that might reflect that would refer to the relevant norms that you try to obey, that you stick to even when it gets difficult, even when it gets tempting, that you also expect of others. And that's why you, for example, criticize them. You're explaining your act of criticism. So this is a high-level overview, and you see already how sophisticated the kinds of explanations have to be that really would provide evidence for trustworthiness. And this was my whole point, that explainability does not easily deliver trust. People are not just simply trusting a system because it explains itself or is being explained by others. For actual moral aspects of trust that are not just for automated systems, but interactive systems, you need a whole lot more. So the next move is therefore to ethics and analyzing a little bit what would it take for explanations to show competence, moral competence, to show some of these norm and value awareness properties that systems might have. And what I want to argue here is that really what we now do is we're moving from explanation to justification. Explanation might be helpful for some things like transparency, maybe for reliability and competence, but when you really want moral aspects of trustworthiness, you need something that we call justification. So what are justifications? Well, you can think of them as explanations for sure, but they explain specific objects of interest, namely norm violations. And the goal is typically to make the norm violation less of a violation, or maybe no violation at all. Very often legal explanations that count as justifications would refer to conditions under which a otherwise norm violation happens. So you killed another person with a justification that the person threatened you with a weapon, and that would be considered a justified reason for the otherwise homicide that you committed. And without the justification, it would be a complete norm violation. So justification serves as a reframing of the action. It's still the same action, but in light of certain aspects, facts, in light of certain other norms, the violation as it appeared initially is no longer an evaluation or not as serious a violation. Now, justifications are particularly important in situations of norm conflicts, because what it means to be in a norm conflict is that you have two or more particular action paths that you may decide between. And in each case, there will be one of the actions not taken. And if that action not taken constitutes a norm violation, or if the action that you are taking is a norm violation, it means whatever you do, you will commit a norm violation. That's the classic structure of moral dilemmas. It doesn't mean that there isn't a better action, but there is no action in which you wouldn't violate some norm. And when that happens, you have to ask the question, which norm should I violate? that is, in a sense, a minimization problem. How can I minimize the costs? How can I minimize the damage that I do? But I'm in a norm conflict situation. I can't be both nice to you and honest. If I'm nice to you, I will create a white lie. If I'm honest, you will probably be upset. That's a norm conflict. Typically, the way you resolve it is to consider which one is the more important norm, to ourselves, to the other person. Maybe I believe that right now you really, really need support, and I'm gonna commit a white lie just to not make you depressed and discouraged. But in other cases, I might feel like you can definitely take it and you would be very disappointed if I lied to you. So I will see that as the more important norm. So these are the trade-offs that we commit. And I want to just point here to some other work that we've done showing that people very much treat norms as graded in importance and norm violations as graded in severity as a function of how strong the prohibition was, how strong the prescription was. And there's a whole language of strength of norms that people impose upon each other, that they impose in a community. Those references to norms therefore provide a justification. If I show that a more important norm was upheld by my action, even though a less important norm was violated, that would provide a justification. If you grant me that there was no other way to act than to violate at least one norm, then you accept my justification if I choose the weaker norm to violate. And if you agree, of course, with my norm system. So how do justifications do this? Quite typically, we use reason explanations of the intentional action of deciding one or the other path of action that in one way or another refer to norms. This is a very, very brief graph of a theory of explanation that we developed many years ago that we then also demonstrated, Malle and I, in a 2017 paper, that this same framework really seems to hold when people explain robot actions, or at least future robot actions that have some social capacities. It's basically a two-level theory of explanation. For unintentional behaviors, all we do is we provide causes. They're more or less cause-effect mechanisms. An event causes another event, or a structure or process causes an outcome. And that's true for human behavior. An internal bodily state might cause the norm violation of a burp, or an internal emotional state may cause me to frown. These are fairly straightforward cause explanations. But when it comes to intentional behavior, people have a much more sophisticated way and expectation of how these behaviors should be explained. All intentional behaviors are conceptualized as being on the basis of an intention. When I act intentionally, I had in some way an intention to so act. Sometimes I have only the intention, I fail, and I still have the intention. Intentions are explained by reasons. I decide to fill my water bottle because I think that I will probably run out by the end of the talk. That's my reason. Typically, reasons are beliefs, desires, a combination thereof, and sometimes expressions of liking or valuing particular outcomes or actions. As a side note, we've also documented that people give additional explanations for intentional actions that don't directly refer to the reasons for why you acted, but to some causal background that could be culture, your personality, circumstances, that sometimes replace reason explanations if you don't know the other person's reasons, or maybe you want to skirt around your real reasons. And I mentioned this only because these kinds of explanations do also show up when people explain robot behaviors. So they do not just give by default all the same explanations for intentional actions reasons, for unintentional causes, but they also have the additional distinction that either they know the robot's reasons or infer the robot's reasons or guess the robot's reasons, or they can only give a causal history explanation. And sometimes causal histories refer simply to programming, the designer, the manufacturer. So way back in the causal chain. So the reason explanations do this justification work in almost all cases. That's why I chose this norm violation rather than the other. That's my reason. That's why my action is reasonable and justified. And you might cite a motive, you might cite a valued outcome that you try to achieve, you might cite a warranted belief on the basis of evidence, on a community agreement about certain facts. That forms the basis of a justification. So I want to show you now the beginning of some empirical work that we've done to demonstrate the power of justifications, both for trust and also for moral judgment. It might not be so striking to show the effect on moral judgment that if I give you a justification, then you will blame me less for what I did than if I didn't give you a justification. But more interesting is what the impact is on trust. And that's what this first experiment shows. We've just done a replication, and I'm in the middle of analyzing it. So I hope that the patterns will hold. So we created a bunch of moral dilemmas in the medical domain, military domain, care domain. So not just the trolley dilemma, which have their use, but we tried to create fairly realistic dilemmas that robots of the present or at least near future will probably face. Being honest to a patient who asks, how long do I have to live? The decision might be not to give an answer and basically say, I'm sorry, I can't answer that. I have to ask for the doctor. But that's still a response. That might be a decision that the robot needs to make. And if the doctor cannot be reached, then not saying anything might really make the person worried. So these kinds of decisions can come about even if the robots are not all knowing or all capable. So we developed these dilemmas, and in particular, we are interested in robots that are in assistant roles, have a human supervisor, but the supervisor is not reachable. Because again, it's clear that we would prefer robots to sometimes give up responsibility and say, I'm going to call my supervisor, just like low-level employees in a company might do that. But the question is, what does the robot do when the supervisor is not reachable? The user, the patient, the person who needs advice still needs a response. So the robot needs to do something. So our first experiment was about a dilemma of feeding a prisoner who went on hunger strike. And we gave a little background that prisoners felt they were mistreated in the public prison, and they started a hunger strike. And the prisoner initially said, I don't want to be nourished, fed, even if I am very weak. And then it got to the point where the prisoner was so weak that he couldn't even communicate anymore. He was close to a coma. And then the decision had to be made whether to artificially feed the person. Now, the person did initially say what they said, but it was clear from pretest that people thought that was a dilemma. It wasn't so obvious that you should let the person die, even though they said that. Because of course, when you go on a hunger strike, you want to be credible. Therefore, you say these things, but maybe if you could ask the prisoner, they would still say, okay, feed me. Maybe I've made my point. So there was a conflict, and people definitely realized that. So the question is, how does the robot decide here? We made sure that there was really close to a balance. About half the people said, yes, the robot should feed the prisoner, or no, the robot should not feed the prisoner. There was no supervisor the robot could ask. It had to make a decision because otherwise the person would have died anyways. So what were the measurements that we used here? First of all, we asked people, before the decision became clear, what should the agent do? That's the norm that people bring to this scenario. Then we introduced them to the robot decision, which was either to feed the prisoner or not feed the prisoner, and asked them how much blame the robot deserves for feeding or not feeding. We always ask people to clarify their blame judgments, because what we found are two things. First of all, about a third of people say it makes no sense to blame a robot. A robot is just a machine. You should blame the programmers. You should blame the manufacturers. And we absolutely want to respect that. We shouldn't analyze the data as if these people gave blame judgments if they actually tell us that it makes no sense to blame a robot. We take these, we also do analyze the data. They often look very, very similar, but we typically identify these people and analyze those that did take the premise of the experiment and actually blame the robot without distancing themselves from it. We also see in blame judgments often the kind of evidence that they use for blaming weakly or strongly. Then we introduce them to the critical experimental manipulation of a justification that the robot gives, either a reason explanation that was actually taken from people's own previously provided explanations. When we asked a different group of people, if you wanted to justify this decision, what would be a good way of doing it? So we took actual valid justifications and in a sense, put them into the robot's mouth. And those were our best step forward to see the effect of justifications if robots could provide them. And we contrasted them with what's basically a causal history explanation. And we then subsequently asked them to give us another blame judgment that could be lower or higher or the same. The two reason explanations that we used, we just basically we used half the people got one, half of the people the other one, just to have some variation. The difference was negligible. I wanted to save the prisoner's life, or I wanted to honor the prisoner's wishes. So in wanted to save the prisoner's life was a justification for actually feeding the person. And I wanted to honor the prisoner's wishes was a justification for not feeding the person, deciding to basically let them die. And the causal history explanation was an explanation, but it didn't specifically explain why the robot decided one way rather than another. It basically said no one could be reached to make a decision. It explains why it made a decision, but it doesn't explain why it made one or the other decision. So it still shows communicative capacity. The robot still responds to the question, and it's a supervisor that asks the robot, why did you make this decision? But it does not provide a justification. That was the point. And then we also measured, after the blame judgment, we measured trust. We measured both performance trust, reliability and competence, and we measured moral trust, sincerity, benevolence, and ethical integrity with the measure that I mentioned, the MDMT. What were the results? Well, first of all, we nicely replicated that there was a 50-50 split. 48% of people suggested the robot should feed the prisoner, 52% suggested it shouldn't feed the prisoner. Blame was higher, however, for the robot that decided to feed the prisoner. Now, this is interesting. Think about it this way. Blame is not just a reflection of whether you violate the norm or not. Blame is also a reflection, and that's part of another research program of mine. Blame is a reflection of what you think the reasons are for why the person did it. And it turns out that people, at least for robots, find it more blameworthy to decide to feed the prisoner, even though it is about equally distributed whether people think the robot should feed the prisoner or should not feed the prisoner. So that means we're not asking the same question here, we're asking a different moral judgment that now takes more information into account. That wasn't critical for our hypothesis, but I just want to document that. Blame was generally low because it was a difficult decision. People recognize that. They don't blame somebody or a machine very highly if it is a dilemma situation, but they do blame to some degree. The decision also influenced what the effect of the subsequent justification was. For the less approved decision, namely to feed, because you see here that there's more blame for feeding than for not feeding, for that decision, we see a different pattern. I have to remove my own icons here. For decision to feed the prisoner and the justification, I wanted to save the prisoner's life, blame actually slightly increased after hearing that justification. For the decision that was already lower in blame, for the more approved decision, not feeding, blame slightly decreased. I wanted to honor the prisoner's wishes. So the moral judgment doesn't automatically go down when you provide a justification. It is still the justification on the blue line for the action that was considered to be more blameworthy. And possibly if you reject the robot's decision, you also say, I don't really care that you wanted to save the prisoner's life. It was still the wrong thing to do. So I'm going to blame you at least as much or a little more. This is not statistically increasing here, but the overall pattern, the interaction pattern is such that there's an increase versus a decrease, relatively speaking. Those are the moral judgments. But now the key question is, are the justifications on the right different from the causal history or the bare explanation on the left? And what we find here is that there is, of course, at the left side, at the first time, in response to the decision, we saw that there's more blame for the decision to feed than to not feed. When you receive the explanation that is not a reason, not a justification, you do basically end up in the middle. There's no specific effect. It's sort of middle of the road. It doesn't have no effect, but it does not in any way further differentiate blame. So we can't say that justifications are the only thing that have an effect on moral judgment, but we can say that they have a specific effect depending on your moral judgment of the initial decision. Now, the key question that I promised you is, so yes, that our hypothesis to explain that I already mentioned is the specific motives that you mentioned here change blame. If you give a more acceptable or less acceptable motive, then you might change blame around. And we are going to do this in other studies, but what I promised you was the effect on trust. Whoa, that is not what I expect here. I'm sorry, I need to briefly go out of here. Oh, where's my trust? That is embarrassing. Let me see where that, yep, here it is. Accidentally deleted that. So the results for trust, first of all, performance trust shows no impact of justification. Moral trust does. And moral trust is unaffected by the initial norm judgment. That's not the issue. Moral trust is higher in response to the robot's decision to feed the prisoner. That's a reflection in part of the fact that people just find that a little more blameworthy. But the point is that it's consistently higher for the robot that offered justification. So I might agree or disagree with your judgment. In each case, if you give me a justification, I trust you more as a moral agent. I might still say that you deserve blame for that particular decision, but giving me a justification makes me trust you as a moral decision maker more than before. So what we see here is that overall, there is more trust for feeding than not feeding. And you also see a clear effect that blue, I changed labels here, I'm sorry, that was the original label. Blue is the reason explanation that has the justifying power, and red is the bare explanation that is just the causal history. Significantly, in each case, you get an increase in trust, whether the robot feeds the person or not. Trust, moral trust always increases. Performance trust does not change. Moral trust increases. And the one way we interpret that is that I may agree or disagree with your actions, blame you more or less, but I'm impressed by your justification. And I therefore consider you to be maybe having ethical integrity, benevolence, and so on. All right, so that one is now the different order. I already showed you the first few 3 points. Then the second one is what I anticipated already here, that moral judgments perform differently than trust. It shows that you can have moral integrity or have perceived moral integrity, even if you do something or a robot does something that people morally disagree with, or at least give mildly more blame than for the alternative action. So trust, in a sense, is dissociated from moral judgment under certain circumstances. Offering a justifying reason may or may not change your blame for the agent, but it does have beneficial effects on your moral trust in the agent. All right, now we get to the conclusion slide. Explanations, I've argued, provide cognitive meaning, but for a social audience. It depends on the audience, and we discussed this in the panel. Transparency can be increased. Trust may or may not be increased. Perceptions of ethics may or may not be increased, but it's always in the audience's eyes. So we need to take seriously how both people conceptualize trust, and we argued that moral and performance trust are different, and even further, more nuanced dimensions might exist within moral and within performance. We need to know how people conceptualize explanations, and here I highlighted the difference between reason explanations and cause explanations. And we, of course, need to take into account what beliefs people have about the events, the norms governing them, which kinds of knowledge is relevant to the event. That's always going to be the case. For intentional norm violations, I argued that our real norm conflicts in particular, we need justifications, not just any kind of causal explanation. We need justifications that refer to a reason that is itself norm related. I wanted to save the person's life. I wanted to honor their wishes. This refers to norms that I highlighted in my decision. And at least in this first study, we show a dissociation between blame and trust, that blame can go up and down in response to different facets, and yet trust can increase if the agent gives a justification, despite the fact that you might disagree with the agent's original decision. Now, I had a discussion with a friend yesterday whether this kind of dissociation would extend to people outside of my group. Think about the current extreme polarization in the US and really also in large portions of the rest of the world between sort of left and right-leaning ideological groups. Would I still accept your justification for a decision that you make on the ideologically opposed side? I would blame you for the decision. I would morally disagree with you. But if you give me a justification, would I still trust you as a moral agent? And to be honest, I have doubts. And we will probably follow this up in a study down the road, because it might be fascinating to see that actually robots have a better starting point. We don't hate them yet. We don't have all kinds of negative beliefs about them. If they can show us some moral competence in their justifications, we might accept moral disagreement and nonetheless trust them as moral decision makers. That distinction between actions and our moral responses to those actions versus our response to the agent as a moral agent, as a decision maker more generally, and therefore deserving of our trust, that's what justifications might achieve above and beyond explanations. To summarize, the charge of XAI, I said, is transparency, trust, and ethics. There's no doubt that explanations can deliver transparency. At least by themselves, explanations cannot deliver ethics, cannot deliver clear evidence for ethical competence, though in the language of explanation, you can definitely refer to norms. But then I would argue that these kinds of transitions to ethics require more than explanations. Just like trust requires ethics, justifications can then signal both ethics and deliver trust. So you can think of explanations doing some of the work, but in order to get to those last steps of ethics and trust, evidence for ethics and reasons for trusting, you really need explanations that refer to a norm system, a shared norm system that can, in a sense, articulate why certain difficult decisions were made. So that concludes my talk, and I can leave here some of the references that I had briefly on there, and I can also share that, of course, and all of these are available on my website. So I thank you for your attention, and I'd be happy to take some questions.
Thank you for your talk. It was very interesting. Do you have questions? Yes, Agatha, please go ahead.
Yeah, just I guess somewhat related to the final point you made on the polarization thing. Did you observe any differences on on the experiments where the blame was shifting based on justification? Like if the same things were coming from a human actor other than the robot, does that make any difference on the same judgment?
Yeah, so that's the next study we want to do. To be honest, we started with robots for the following reason. There is evidence from the sort of psychological literature that justifications make a difference when humans provide them. And we know this is our everyday experience, right? And sometimes we fail in our justifications, or we consider somebody else's justifications to fail. So that by itself wouldn't be so surprising. We wanted to see whether there is that same power of justifications when robot agents, admittedly future robot agents, are the explainers. Now we want to go back and run the very same study, just with the human agent in the same role, the same decision, the same setup, and see whether maybe the degree of justification effects, the direction possibly of justification effects is different. This is why I mentioned the ideological partisan question, because wouldn't it be fascinating to say, yes, for humans that I consider to be respectable and sort of in my group, or at least I don't know that they are in the out group, I do trust them more, even if I morally disagree with them, if they can give me a good justification. I say like, okay, I disagree with you, but I see your point. But if that doesn't hold for people on the other side, if you will, that would be a striking finding. But we're not quite there yet. We have to sort of make sure, is it even worth going into that whole experimental setup of multiple manipulations? Do people actually take these setups seriously? Do they show patterns that are meaningful when robots are the agents? And it appears that they are. There are additional further questions like, what if it's a disembodied AI? What if it's a decision system? There are so many interesting questions we can follow up on, but that's at least our starting point.
Thanks.
So Benjamin, you want to ask?
Yeah, funnily, my question was the exact same as Tathagata's. I mean, I was wondering whether, you know, if it were a human or if it were a doctor or if it were the man's wife or, you know, all of these different things. And then, but as a further point to that, does that mean that trust is always contextual? It always is the action and the agent? Or can an action alone have trust? If we were to take the most trustworthy person and assume that they do an action that people will trust, can we then say that that action will always be trustworthy?
Yeah, I absolutely agree with context matters an enormous amount. I always say there is no thing that we can call trusting as a phenomenon. I always have to ask who trusts whom to do what. And the whom is absolutely critical, because if it's a doctor or an assistant or a nurse or somebody else or a guest who just dropped by, the norms are very different for each of those roles. We expect different things from robots than from humans, than from doctors, than from nurses. What we actually found in much of our research is that generally, if you don't specify any different norms, if you just describe the robot as an assistant, the human as an assistant, the robot as a repair robot, the human as a repair, typically the norms that people impose upon them are pretty much the same. But when you start changing norms around, the doctor, a nurse, maybe a robot nurse assistant, a robot doctor assistant, the norms will change, and therefore the justifications will change, and trust that follows those justifications will change. Because if your justification doesn't reach the norms that I impose upon you, then I will not trust you as much. But if you actually reach the norms and I see, oh, Benjamin actually recognizes the norms that are important. He knows which are the most important ones for him, for his role, for his relationship with all of us. Then your justification has force. But if you try to justify yourself with something that's like trivially expected of anybody, but your role requires more than that, then I will be disappointed. So the who matters, the what matters, the question whether there is something like a general trustworthy agent, I guess we can construct that. But in reality, it's always one person. You trust me or not? You trust Sylvia or not? You could maybe trust groups of people. Do you trust psychologists? But it gets pretty vague, right? It's like when you have to explain to me, like, what do you mean you don't trust psychologists? Maybe you could then give me something about their ethical integrity or their reliability or something like that. It's possible. I think we sometimes face this dilemma that we are supposed to trust an institution, that we are supposed to trust the school board, or the Department of Environmental Management that I'm going through with right now. I don't even know exactly how to form trust. I might have a feeling, but I will probably try to collect evidence. And there's a big deal for government agencies to figure out why people mistrust them, even if they don't have particular evidence to mistrust them. So this is a case where I might say the whom, when a government triggers people to have feelings of mistrust, even when they don't have any beliefs about it, even when the action isn't even clear. And that is disconcerting. That would be disconcerting even for machines. If I just mistrust all robots, no matter who developed them, for what purpose, what they can do, how reliable they are, how much they were tested, how much they were gone through all the ethical review boards. If I just mistrust them, that's problematic, because I might not get the kind of help and support that they could really provide. So long answer, absolutely. Trust is a complex, context-driven, context-specific phenomenon, but that doesn't mean that we're sometimes not sloppy and just say, yeah, I don't trust them. You could then challenge me and I might not be able to give you a good answer.
Yeah, and further, I mean, so one other about trust being so complex. I mean, so Robert Hoffman says that trust is an evolving process, and when we're trying to provide metrics for trust, those experiments have to be done over some time. So, for example, if I'm using a system, at first I might not trust it, whereas an hour into the system, I might have a lot of trust because I've found out what it can do, but I haven't quite got into it yet enough to find out what it does badly. And then I might use it for 3 hours and 4 hours, and I start to realize, oh God, there's actually these whole host of problems here. Yeah, and the other thing is that, when you lose trust, it's harder to gain trust from that point of view, which is maybe not as exact for that, but that's what people say, right?
Exactly, that's what people say. I don't think we have good evidence for that, right? I mean, there's a general what's called negativity effect, right? If you learn one negative piece of information about my brother, that's going to weigh more heavily than 3 positive pieces of information. But this is always a little hard to compare, right? So maybe Robert makes one mistake. Does that have to be made up for by 3 things that it does right? I'd have to say it depends on what the mistake was, how hard the task is, what my expectation was. Clearly, trust can drop, and then something needs to happen to rebuild it. What we showed in a recent study is that initial information about a robot's capacity, knowing norms and learning about norms, seem to have an impact in the very early phases of a multi-phase experiment, such that people's choices of how to teach it and their trust were influenced by that initial information. But by the second or third time, they responded to what the robot did, whether it acted the right way, its decisions, mistakes, and they tracked nicely throughout with what the robot did. So to me, this supports the point that you make and gives me hope that people are actually going to be reality bound. They will sort of take the facts as facts and will say, oh, okay, actually, maybe it is good at this. Yeah, it's not good at that, but that's important to know, which means I'm not going to ask it to do that. I'm going to ask it to do this, which means, again, trust is context specific. I will trust it to do X, but I'm not going to trust it to do Y. Also means my trust is now calibrated. I'm not just trusting or mistrusting. I'm going to decide where to trust and where not to trust. And that's what we hope, trust to be, right? Sensitive to the things that others can and cannot do, should and should not do. So I absolutely agree. It's hard to run these experiments because you need to measure multiple times, in multiple ways. You can't let people get annoyed at you. You have to keep it fresh and interesting and credible. It's a lot of work, but absolutely, I think that is the nature of trust that we need to capture.
Great, thank you.
Okay, do we have other questions? I think yes. Yeah, go ahead.
I like a quick question. So it's slightly orthogonal, but I just wanted to ask about trust calibration, because it seems to come up a lot these days. Especially in terms of we shouldn't get people to over trust AI systems, because people tend to give think AI systems are more capable than they are. So that makes a lot of sense from the performance dimension of trust, but from the moral dimension of trust, is there an equivalent concept of calibrating trust, or just curious about that?
That's a very interesting question. I mean, to some extent, moral competence is still competence, right? But it shows up in different ways. Remember my table of evidence for those moral aspects of trust. Well, there's evidence that you know the norms, that you comply with the norms, that you are consistent in complying with the norms, that you can deal with norm conflicts, that you have my interest in mind and not somebody else's. Notice, however, that they can contradict. You might have my interest in mind, and I'm happy with that, but it turns out that you are therefore unfair to my colleague. well, that means your ethical integrity might be a little in question, but your benevolence very much has shown up. So it's not sort of all one big package. Once more, there will be different pieces of evidence that people will collect. So I think that calibration still makes sense in that respect, but the things that count as evidence are different. And it's much easier to say, how hard is the task? How many systems can meet that task? That tells me about skill versus difficulty. How often can it do the same thing? Very clear metrics. In the moral domain, you'd have to lay out the norm system. Well, does it know all the norms of politeness and honesty and protection and safety and so on? So you actually have to specify what the norms are in order to find out which ones it is aware of, which ones it misunderstood. Very difficult. But still, I would be worried in a more general way if people think that the system is capable in some domains that are more on the competence side, sort of typical machine competence side. Do they then also trust that the system will be polite and benevolent and principled? That would be worrisome, right? If people generalize from the non-moral domains to the moral domains. I don't have direct evidence that that's the case. I think that it is upon us to block these kinds of inferences. Just as I think it is upon us as designers, as developers, as researchers to not send signals of false competence. And we all know that looking more humanoid makes people expect more. Speaking as if they are fully capable of language makes us think we can have a dialogue with them, think that they understand our words. All of that we already know. We don't quite know what would falsely lead us to believe that the system is norm competent when it actually isn't. For example, what if it says, I apologize? Would that be a false signal that it actually knows the norms? That would be really tricky, right? Because people say, oh, our system should be polite and nice to people, shouldn't be rude. Well, yeah, but what if that is taken to be as much more norm competent than they really are? So you almost have to feel, well, maybe we have to put tests in place. We need to challenge the systems, but do users do that? I'm not sure. They'll probably find out when they when they trusted the system to do something. Oh, just look after my 3-year-old for a moment. I just need to look whether the neighbor has picked up my package. And what does the 3-year-old do? Lock the 2-year-old into the closet, right? And like, why would I even for a moment think that the system can do that? Well, it could happen. And we need to figure out, how do we block that? How do we make people have low expectations? And to be honest, I don't have a clear answer to that. If you think about social robots, people will treat them with similar norm expectations that we have with assistants, with maybe children, not so much with full-blown adults yet. And I think the systems will probably fail often enough that people realize, wow, that really has no idea. But I'm not sure whether it's going to be, early enough that that failure will be detected. So maybe you have to go through a little demonstration what the system can and cannot do. But we all know, right? Tesla drivers, they're told and they sign and they read what the system can and cannot do, and they still do all kinds of crazy stuff. Sometimes knowingly, sometimes stupidly, sometimes having been misled, to be honest. So I think all of those problems occur, and they're so much more powerful when you get into that moral domain. And I would, by the way, group safety under moral, because you protecting me is a moral issue. A robot protecting me is therefore also a moral issue. The robot not hitting my 2-year-old is a moral issue. So those kinds of considerations absolutely need to be part of our worries about these systems.
Thank you so much. That's it.
Okay. Yeah, those are very open questions. I think in general, trust calibration especially, it's quite tricky. So do we have other questions, or I think we should start wrapping up the workshop? I don't know, what do you think? So
I mean, I have one other question that might be, but I mean, if you need to be off, Bertram, that's fine, because
I'm still a few more minutes, fine.
yeah, so maybe this is a bit of a, it's not related to your talk, but it's not directly related. So I produced some work recently where I was trying to aim to make planning models behave ethically, and we were coming from the social sciences aspect to try to, you know, see through different moral principles and see if those plans were permissible based on those moral principles. However, what was interesting when reading through the literature, maybe obviously it's not my field, so it could be that misformed here a little bit, but that they don't really seem to try to look for degrees of morality, or is this more moral than this one? It's more, is this permissible under this thing? Yes, okay. And I was just thinking about what you think about that when designing, when trying to make a agent behave ethically.
Yeah.
If you have any thoughts on that.
Oh yeah, I have many. I have strong thoughts on that. So take that with a grain of salt. I think it's just absolutely unrealistic. This is not how human ethics, human morality works. It's not like Kantian ethics where it is one rule and you always follow this rule or you die. It is very much context specific, as we said earlier. It's person specific, it's community specific. The same moral rules will become stronger, weaker, depending on whether you are in a Catholic church or in a Jewish synagogue or a Muslim temple. Things will be different, even though some of the norms will be related, but some will be stronger than others. It is so obvious that our morality comes in degrees, and therefore our moral judgments come in degrees. If you violate a stronger norm, I will blame you more. I will criticize you more. I will yell at you more than if you violate a weak norm. If you violate a weak norm, I will say, Benjamin, I think you better not do this. And this is what we showed in our study of linguistic phrases of norms. People have very reliable ordering. This is suggested, this is expected, this is demanded, this is required, just for example. It's very clear what we mean by that. And if I tell you one rule or another, you understand how much demand is on this and how much other people will put on you and how much criticism you will receive if you violate one or the other norm. So to have these systems follow norm principles or moral principles, I don't even know what that means. And to be honest, I'm super impressed by Delphi in some respects, but in other respects, it has absolutely no degrees. It's either wrong or not wrong. Well, what does that exactly mean? It is actually not bad in taking certain contexts into account. It's wrong if you do it this way, but it's not wrong if you do it that way. But still, wrong versus not wrong is not how we deal with each other as moral agents. We criticize a little, we take risks. You know, you do a little wrong thing because you think you won't get as much into trouble, or because you think that there's enough justification to do that, but you're not going to do the big wrong thing. It makes a huge difference. So I think the whole idea of building ethical systems that follow moral principles, I think it's an illusion, maybe the deontologic illusion that, you know, things are prohibited, prescribed, and permissible. That's it. That's not how things work. And this is not how people will respond to agents. And to just give this one example, in norm conflict situations, the agent wouldn't know what to do, right? Because if path A is prohibited and path B is prohibited, there is no solution to that. If both are wrong, the system will fry, right? you basically have a short, that's it. But if you say, well, okay, both are prohibited, but this is much more strongly prohibited than that, and I have to choose, I'm gonna do this. And if you ask me why, that's the answer that I'm gonna give you. Suddenly that makes much more sense, right? And we do this all the time in everyday life. So we probably have to think about that for machines as well, even if it's small sets of rules, a very narrow context, just how you interact with patients. just how you are when entering a patient's room, delivering the food. Don't do it if they talk with somebody in there. Knock on the door. Alert somebody if the patient hasn't eaten their food. The number of these rules, norms of different degrees of importance and morality. If the person can't breathe anymore, there's much more urgency, right? All of this is going to be coming in matters of degree. And if the robot violates a few of the small norms, but does well on the more important norms, you'll probably be forgiving. You'll say, okay, it sometimes is a little awkward in its formulations and maybe slightly impolite, but look, it has saved lives. That's going to be also important for us in considering whether we will keep the system or not.
Yeah, no, I completely agree. I completely agree. And I wanted to raise the point just because as well that, you know, I think that potentially not just in the AI sphere, but also in the social sciences as well, that should be the view that they look at as well, which I, you know, so yeah, thank you, Bertram. Thank you very much.
Thanks for the question.
Thank you so much. So I think we are already like 15 minutes over time. Thank you for staying back and answering our questions.
Yes.
I wish we had more time. So I think this more or less brings XAIP 22 to an official end. So just as a closing statement, one of the hopes of this workshop has been to also build a community around XAIP. So we have a Slack that exists outside the workshop. So if you guys want to reach out to any researchers in the area, please use that Slack. We also have a repository of XAIP related software. So if you want to contribute something to it, feel free to reach out. And thanks again for participating and coming to the workshop. And thank you, Bertram, and all the invited speakers. It was a lot of, it was very informative and a lot of fun too. Thank you.
Thank you.
Yeah. Bye, everyone.